Well, first of all, I want to welcome you all here to Cornell and to Chess. It sounded like some of you had maybe a somewhat eventful trip here, and so I'm glad you all made it. So kudos for that. Let me just flash up our schedule here for the next couple days. So we have a pretty eventful workshop planned for you all here over the next 2 days. The schedule here is up on the screen. Basically today we'll be focusing on kind of teaching lectures to give you all an introduction to both what is a synchrotron, this massive machine that we have built underground on campus here, and then how can it help you all answer the kinds of research questions you have in chemistry, materials, and physics. So that'll be one for today. We'll close out today then with what is maybe the most important part of this, which is how can you write a proposal to use a facility like Chess? You know, Chess wouldn't exist without users like you all, bringing exciting science for us to help you with. So at the end, we'll show you how to write a proposal to do those kinds of experiments in collaboration with us. And the second day is probably the more fun of the 2 days, where we actually get to go down to Chess and do experiments at the beamlines. So we have 4 different demonstrations based on the techniques that we're showing you today. You'll all get to pick to do 2 of those different demonstrations. So whoever's talk you like the most, you can sign up to go to their beamline and see what those experiments are actually like in person. We have a poster session tomorrow too, so you'll all get to hang out in a little bit more of an informal environment, get to know each other some more, and yeah, it should be a pretty good workshop. Then I'll leave you with probably the most important part of everything I'll say up here now is please ask questions. You know, we're all up here today so that we can, help all of you to understand what we're doing here, so we like questions. So please ask us questions, don't be afraid. There are no stupid questions. I've asked dumber questions than anyone else here, I promise you that. So don't be shy. Any questions at this point? Before I go ahead and transition in? Okay, well, it's like that then. Our first speaker today is Jacob Ruff. Jacob is the director of the Center for High Energy X-ray Sciences here at Chess. He used to run one of the beamlines until just about a year ago. He became director. And today he'll be giving us an introduction to synchrotrons and X-ray science. So, without further ado, it's all you, Jacob. Thanks.
Thank you very much. I should retroactively introduce Chris Pollock. Yeah, so Chris Pollock is organizing the HEXT workshop this year and has for the past 3 or 4 years. So thank you very much, Chris, for getting everything together, bringing us all in here, and keeping the show running along with Mike Gilpin and all the support staff that's here. Just thanks very much. So my name is Jacob Ruff, and I'm really excited to talk to you for a little bit this morning. I have you for about 45 minutes. I'm going to try not to run long, although notoriously I do, so I might end up getting cut. I'm very excited to be part of this summer school, and I have been for a few years. Sometimes I end up thinking about the way I first found myself at facilities. I realized that when I was in my first year of grad school, a master's student, I went to a scattering summer school for a facility that doesn't even exist anymore. It was called the Chalk River Scattering School. But that was my first introduction to the idea that there exist these huge facilities that are full of scientists who spend all of their time trying to help users from universities come in for 3 or 4 days to advance their research. So that wasn't something that I really knew about before. And I got a chance to go and visit and try some of the beamlines, and that sort of changed the course of my career. I've spent my entire career at user facilities versus a user, as a grad student, postdoc, and then sort of working as a staff member at them. So hopefully we can give you a little bit of a flavor over the next couple of days of what life is like at a user facility and why it's an interesting place to do science. And get our hooks into you a little bit so that you come back as users and join our community. Okay, so I'm generally going to try to give you just a sort of quick overview of what synchrotrons are and why we care, why we go to all this effort to make these very bright X-rays, and sort of that's my job for this morning. And then, as Chris said, I'm going to hand off to a series of our staff members, the members of our scientific staff here. We're going to talk about different sort of specializations or techniques people use to advance their science. So later on today, you're going to hear from Alan Das about what we call scattering, from Louisa Smeska about X-ray imaging. You're going to hear from Chris Pollock about X-ray spectroscopy, which is his expertise. And we're going to hear from Jenny Wireman about crystallography, and specifically a little bit about protein crystallography. So I I confess that I believe I have the pleasure now, as I get more and more gray hair, of being able to say that I knew all of these scientists when they were students. I've seen them, become real parts of our, our scientific leadership. So that's very gratifying. And so I just want to point out, we're always focused on, CHEST is really focused on teaching and developing this community. And so hopefully I'm in a room full of other future synchrotron scientists. Okay, so today, oh, by the way, I'm trying to do this without a mic, but if anybody has trouble hearing me, just let me know. I can always mic up. So today, the goal is to sort of generally cover, how do we generate these really bright beams of X-rays, and why? Why do we want them? How do we use them to study different problems in materials chemistry, manufacturing, etc. That's kind of the topic. My goals for you, for this talk, but also for this whole workshop, I guess, are to help you become sort of informed consumers of X-ray data. Because X-ray data, you're going to encounter it whether you decide to use synchrotrons or not. When you read papers, when you read the literature, you're going to see other scientists saying, they'll show some data from the synchrotron and then they'll make a scientific claim. And you want to be sort of a sophisticated consumer of that. You want to look at it and say, well, is that really what this means? Or are they just trying to show me something flashy from a big machine and convince me, So hopefully you guys will get some new context for all these measurements that you're going to see in the literature anyways. I also hope that you learn about some techniques to be useful for your research and that we can actually help you move your science forward. And lastly, just sort of how play matchmaker and identify, you're going to see sort of the anatomy of how we talk about these labs, but basically we have different beam lines that do different techniques that are appropriate for different problems. So to help you sort of sort out, well, if I want to answer this question, where do I go, what do I do? That's sort of the goal. The outline of my talk, basically I'm going to give you an introduction generally and very quickly to synchrotron light sources, and talk a little bit about the properties of X-rays and beams of X-rays, sort of the distinction between those. We'll talk about how X-rays interact with electrons and materials at a very 1,000-foot level. We're not going to get too deep in the weeds. We're not going to do a lot of math. But just getting a general idea of how the interaction happens. And then I'll talk a little bit about CHEST, which is the facility where we work, which is an example of synchrotrons. And a little bit about how what we call a beam line sort of comes together and what the techniques are. So that's the goal. Okay, so let's talk about synchrotrons and light sources. So worldwide, and this is a picture that's stolen from a website called lightsources.org, which has a lot of interesting information. Worldwide, there's more than 50 accelerator-based light sources, right? And they're sort of all over. There's a bunch in the Americas, there's a bunch in Europe, there's a bunch in Japan, there's some in Australia. So really, this is a huge international effort. In the Americas, there are several. They're sort of concentrated at many of the DOE labs, so CHEST is here at Cornell. At Argonne, we have something called the Advanced Photon Source. There's the Advanced Light Source, which is at Berkeley on the West Coast. Brookhaven, which is on Long Island, has what's called the National Synchrotron Light Source. SLAC has 2 light sources. There's the SSRL, which is synchrotron. They also have a free electron laser, which is a sort of massive creation we can talk about offline. There's also a Canadian light source where you have the Saskatoon. There are light sources in Brazil. So there's quite a span of these sources. I guess one thing I want to impress on everybody before we get too far into it is it's sort of like a massive investment in science. This constellation of light sources. If you look at the total expenses in the U.S. on building and operating these light sources, in very round numbers, you're talking about something like $1 billion a year. This is something that they put a ton of resources into. And what's interesting about that is they're almost exclusively run as free, not free for the government, but free for the users. So for the people who want to come and do their science, you can write a proposal, and if your proposal is deemed scientifically interesting, you can just go and use all of this equipment to push your science forward. So that's like a really exceptional, tool that's there on the table for you to use, right? They're also very interdisciplinary, so they don't tend to be built to do one thing. And because of this peer review process, different disciplines of sciences kind of duke it out to see who can get time. Who can write the most interesting proposal, which communities can be the most engaged. And so, the more engaged you are with light sources, the more of this, huge resource you can sort of pull towards the science that you guys are interested in. And so that's my pitch for why just about everybody should be interested and involved in the light source. All right, so, but why? Why do they spend all this money? Why do they build all these light sources? What is the point of this? So, a slide that I stole from my director, I think I saw him walking a moment ago. So what is interesting about X-rays anyways? X-rays are basically just light, right? But they're short wavelength light. So, if you look at the spectrum of electromagnetic radiation, long wavelengths, you have things like radio waves, microwaves, you have visible light in the middle, of course. And then as you get shorter, you get into the sort of X-ray gamma ray regime. So these are very energetic, very short wavelength photons. And they're useful. They're useful in a way that I think everybody kind of intuitively knows. They penetrate deeply through things, right? So if you go to the dentist, you can get an X-ray of your teeth, you can do this radiography. They give you an ability to see inside things. So they're really good for probing matter on very different length scales. You can go through a shipping container, you can look at the distances between two atoms. And then it turns out that these light sources that we know how to build, these accelerator-based light sources, are incredibly bright. And by bright, so this plot is a little busy, but here is sort of like energy of X-rays and a measurement that's a little bit colloquial, but we basically call brilliance. We can think of this as just like how bright is a light. And so down here, the sort of X-ray generators that you could make in a lab, the things that you'd have for a radiograph at a doctor's office, you have sort of 10 to the 10. This is a log scale. So these accelerator-based light sources like CHEXT that you can see today and tomorrow are kind of up here. This is 10 to the 20. So this is 10 orders of magnitude brighter than the kind of X-ray that you get at the dentist, right? And so the distinction there is sort of between one candle and, I guess 1 candle and 10 billion candles, or 1 candle and all the lights at a football stadium at that rate. So these are enormously bright light sources that we can build at Synchrotrons compared to what you can build in the lab at home. So my argument, and I'm willing to be argued with, but hopefully over the next 2 days we can kind of convince you, is that X-rays are actually the most versatile tool that exists to measure the properties of basically any physical system you care about. All right, I really believe that's true, and that's the reason why every community from cultural heritage to biology to engineering to physics to materials are all huge users of synchrotrons. And the beams that we can make at these accelerators are just incredibly bright, right? And so because you have those two things, you have all these wide applications in many different kinds of science and technology, and that means that basically any advanced economy, any G20 nation, they will look at this and say, well, we have to have our synchrotron. And that's why you look around the world and see 50. Okay, so that's my general pitch of why these things exist, why they're important, why you should care about them, hopefully. So I'm going to switch gears a little bit, and I'm going to talk about X-rays, the properties of photons, the properties of beams of photons. And there's a distinction there. So if you have just one X-ray, it has a pretty small number of physical properties. There's not that many characteristics that it has. It has an energy, and it has a wavelength, and those two things are tied in directly to each other. So the longer the wavelength, the lower the energy. It has polarization, which is basically telling you how the electromagnetic fields are oscillating, which direction, and it has a direction. It's flying through space in one particular direction, so it has a vector momentum. That's kind of it. Those are the properties of a photon. Now, if you have a lot of them, and I just tried to convince you that we do, in fact, we tend to talk about having sort of trillions of photons per second in tiny spots, then you have different set of properties that you talk about for the entire ensemble, or the whole beam of photons, right? And so those properties are sort of related to these ones, but they tend to be a measure of, how similar are all of these X-rays. So we might, instead of talking about an energy, we might also talk about a bandwidth, which is, if you look at all 10 trillion of your photons that are in your beam over a certain amount of time, how much do their energies vary? How perfectly set is the energy of that beam? You can have size, right? How big is that beam? Are they taking up this much space, or are they taking only a nanometer of space? If each one has a polarization, if you average over them all, what's the average polarization? Can you prepare them all to be polarized the same way? Basically, one important number is just how many there are, and we talk about that a lot. How bright can we make that beam? There's also something called coherence, And coherence is a little bit tricky, but it's something that you're familiar with probably if you've dealt with lasers. So laser light is very coherent, light from a candle is not. But basically that means, as you have the waves of these different photons, are they perfectly matched in phase? So that they can interfere constructively with each other. And typically there's sort of a size of the beam over which they are phase matched. That's what we call the coherence line. So you hear about that a lot if people talk about different kinds of coherent diffraction. And also, synchrotron sources, this is a subtle thing, but the light is pulsed. So it's not a continuous beam. It tends to actually come in very fast flashes, which repeat. And so those pulses have some length, right? And that will tell you sort of the resolution if you want to measure things very, very fast. So typically our pulses are about 100 picoseconds long, and that means that we can, we can look at really fast dynamics on sort of sub-nanosecond time scale. Okay, so just some general background, properties of photons, properties of beams. These are numbers that you're going to hear about a lot if you hang around the synchrotron community, so it's good to have some context. Just sort of, I don't expect you to retain this, but these slides will be online, but just sort of a basic background of what's sort of attainable at synchrotrons. The energies that we work at tend to be from sort of kilovolts to megavolts, which are similar to the electron binding energies. So these are similar to the energies that stick electrons to atoms, right? And that's important for spectroscopy. You're going to hear about that later. The wavelengths tend to be sort of nanometers to picometers, and this is like atomic scale. So if you think about the size of these waves, they're sort of like the size of the distances between atoms. Bandwidth we can actually play with a lot. We can sort of control it as we like, so we can tune the resolution and resolving power of our beams, which is nice. Beam sizes tend to be sort of nanometers to centimeters at synchrotrons. Divergence, these are sort of angles, microradians to milliradians, depending on how you set your beam line up. And pulse lengths, like I said before, are sort of picoseconds. Polarization, we can pretty well control to be anything we want. We can make linearly polarized light, we can make circularly polarized light, we can control it quickly, and that lets us do different kinds of spectroscopies. And coherence lengths tend to be microns. And so, we can, depending on how the beamline's set up and how exclusive you are about which photons you allow to pass through to your experiment, sort of 10 to the 9 to 10 to the 14 photons per second are kind of reasonable. So back of envelope, these are the kind of numbers that we can generate for all the different kinds of experiments that we want to do. Usually, at least historically, when we would do these kinds of summer schools, we would hand out copies of this like hard X-ray data booklet. I don't think we actually have physical copies anymore, but you can download them. This is actually a very useful little handbook that people used to carry around in their front pocket, which never looked cool, but it was still cool to have them because it's actually full of a ton of reference information about how synchrotrons work. It has things like tables of all the electron binding energies, details of how synchrotron radiation works, optics, things like that. So I encourage any of you that hope to hang around synchrotrons in your life to get yourself a copy of the data booklet. Okay, so summarizing, some key properties that make high energy X-rays powerful probe. So they can penetrate deeply into a material, they can probe things like the average structure and the chemistry. They interact really strongly with electrons and the charges, and they interact pretty weakly with things like spin and nuclei. So really they give you a nice probe of what the electrons are doing in the material, which is usually the most interesting part. I mean, maybe I'm biased, but as a matter physicist. You can sort of prepare your beams to order if you're clever about how you build your X-ray optics, and we'll talk a little bit about what that looks like later. And it's also very useful that the energy and the wavelength are naturally matched to the binding energies of electrons and atoms and also the distance between them. That makes them a really natural probe for what's going on in materials. All right. And because beams are bright, we can perform measurements very quickly with high precision. So that's the pitch for why we do this. So before I roll on to talk about sort of microscopic X-ray interactions with matter, are there any questions about any of this? Yeah.
Is it a destructive technique or not destructive?
Well, it's not perfectly non-destructive, but it's quite subtle. So most materials are not horribly damaged by our X-ray beams. However, Some materials, so biological materials, of course, are, right? So we would not want to put a person in our X-ray beam or any living thing, or at least, I mean, there's some, we do not currently put any living thing in the X-ray beam. Maybe some plants, right? We put a few plants in. If you put things like protein crystals in, which Jenny will talk about later, I think a little bit, you can see damage. So like biological tissue macromolecules, the beam can charge some parts of it up and they'll actually change how it interacts. So you can damage things with the beam, but it usually takes a little while. And if we're careful, we can usually probe a material in its undamaged state. Their free electron laser that I mentioned quickly, that's a slightly different story. They, this device in California, which is a very, very long, basically incredibly bright, the brightest X-ray source that we've ever built. It does tend to obliterate things that you put in, and so you sort of have to like diffract and then destroy. So as long as you get the information out fast enough, like a few femtoseconds, that's fine. But with synchrotrons, most things we put in are synchrotrons.
And can you clarify what it means that an X-ray is bright? What does it mean?
Yeah, sure. So for me, brightness means something very specific, and basically it's, so if you have a beam, right, it's how many X-rays you have in a sort of certain small angle subtended by the beam, or a small spot in a small amount of time in this a small range of energies. So if I make that acceptance as small as I can, I try to make be really, really selective of which X-rays I let through, how many are left. That kind of makes sense? So a bright beam is a beam where all of the X-rays are almost exactly the same. Almost exactly the same energy, almost exactly the same direction, almost in the exact same physical spot, so the spot size is small.
Okay, yeah.
So conversely, a beam that's not bright, they would be going in every direction, and they would all have different energies, sort of like a light bulb, right? Okay, so we're not going to belabor this stuff, but it's worth thinking about what actually happens when an X-ray hits stuff. And mostly what it interacts with, I said this before, are the electrons in the material. It interacts most strongly with those. And the way it can interact with them is, at least with a free electron, it's pretty simple, right? So the main thing you can have what we call sometimes elastic scattering, sometimes Thomson scattering, usually elastic scattering. But just imagine this. You have an X-ray that comes in and hits an electron, and they're going to have some kind of interaction, and then they're going to both go on their way. And the simplest thing that this electron can do is it can just sort of wiggle back and forth with this X-ray that came in, and then re-emit. And it re-irradiates in sort of any direction, like a spherical wave. So it turns out that the scattering for that is completely isotropic. If this thing is polarized, then it doesn't like to scatter in the direction it's polarized, but otherwise it just comes out in every direction. It doesn't change energy. So that's elastic scattering. That's sort of the simplest thing that can happen. Now, you could also have inelastic scattering, right? So if we're going back to sort of high school physics classes, where you can come in and you can hit this thing, and this thing can recoil, and then you can have your X-ray come off in a different direction. So you transfer some energy and momentum to the electron. So we don't have to get into that. This problem is actually, turns out, a little more complicated to calculate than you would expect it is. But it's been done, of course. Most of the stuff's been sorted out, and you can figure out what the intensity and energy of the X-rays that come off in all different directions are. So that's called Compton scattering. And those are kind of the only things that can happen if you have one X-ray interacting with a free electron. But most electrons in the world are not free, just wandering around in space. Almost all of them are stuck to atoms, so that completely changes the energy. So when you stick these electrons onto an atom, they're bound there in some kind of orbital, and so they can still have inelastic scattering, but the energies really matter. So if you come in with an X-ray that doesn't have enough energy to knock that electron out, to release it from the atom, then you can still elastically scatter, but it's going to change the way it vibrates a little bit. If you do come in with enough energy to knock that electron out, then you can do things like create holes and have all kinds of other inelastic processes. But basically, this is sort of the more complete picture of what's going on. But the point is you still have elastic scattering, and it's still kind of the dominant term. So what are the actual things that can happen if we have an X-ray that comes into a material? So I'm going to argue that there's kind of four, right? And I'm doing this at a cartoon level. You know, X-ray comes in, interacts with the material, scatters off at some angle. We call that 2 theta for reasons that I'm sure going to explain later. You know, so you can also have these processes where, you know, if you start interacting with electrons at energy levels, you can sort of pop them up into you know, high levels by absorbing an X-ray and drop other things down into holes. So elastic scattering, which was the simplest thing we talked about before, we just sort of like interact with the electron and it re-radiates in any direction. It turns out that that's enormously powerful as an experimental technique. So if you actually just go through and measure, you know, all of the X-rays that scatter off of a material, you basically have built a machine that takes a Fourier transform of the electron density of whatever you're looking at. And so that tells you a huge amount about where the electrons are physically in space inside your sample, right? And so we call that diffraction. And you're going to hear about it both from Alman and from Jenny later today in terms of the power of that technique, elastic scattering. Now, conversely, if instead of doing this elastic process, you have absorption and emission processes, that's also hugely powerful, but it tells you about different stuff. So that's just to tell you about electron binding and chemistry in your material, right? And so both Chris and I think Louisa will talk a little bit about completely different things you can do with this part of the cross section. You know, but basically in this case you're talking about you bring in an X-ray and you're going to take one of these electrons, you're just going to kick it out, send it screaming off into, you know, what we call a continuum or something like that. And then, you know, very short while later, because now you have a hole here that's highly energetic, one of these other electrons is going to jump down and fill it. When that happens, it's going to release some energy. So it's going to release a new X-ray, lower energy. And that new X-ray that comes out tells you about sort of what this electron was doing before it popped back down. Right? So it gives you sort of a local probe of what the energy levels of the electrons are. So both absorption and emission. So the probability for being able to knock one of these electrons out of its home, and then the emission process where that hole gets filled up by some other electron. Both those have huge amounts of information about the chemistry of materials. And the chemical composition, I should say, of materials, because each atom has sort of unique fingerprints for this stuff. There's also something that you're not going to hear at all about today, but I'm going to talk about it because it's like near and dear to my heart. There's something called resonance scattering, which is kind of a combination of these two. So if you tune exactly to an energy that's just the difference between an occupied and unoccupied state in an atom, there's a resonance there. And you can get these processes where you sort of scatter elastically, but in the middle of it, you virtually hop one of these electrons briefly up into an empty state and back down. And when you do that, you start to get these really weird effects of being sensitive to things that are going on at this highest energy level. And this tends to be where interesting things like, you know, if you're interested in quantum materials, magnetism lives up here, charge density waves live there, it's close to the Fermi energy. So you have all kinds of, like this resonance trick gives you sensitivity to stuff that you can't usually see. And so that's a process that also exists. Sometimes you'll hear this stuff called REX and RIX, so that's resonant elastic and resonant inelastic scattering. Like I said, we're not going to talk about that over the next couple of days, but these are cool techniques that you guys might want to investigate as you move on. And then there's also inelastic scattering. I gave you the example of inelastic scattering, which is the boring one, which is just a free electron, you know, recoiling. It's Compton scattering. But you can also, if you come in and you're very careful with the resolving power of your beam, you can see every little amount of energy that you deposit into the sample. So you can watch X-rays come in and leave the sample, but leave something behind, some excitation, like a phonon or an exciton or some other weird thing that exists in the material. So if you are very careful, you can look at how much energy momentum you give to the sample, and then you can figure out what excitations exist in it. So that's an elastic scattering. Again, we're not going to hear a lot about that today, or really anything. But these are techniques that are out there. Things like quantum scattering, high resolution inelastic, which is a way to look at photons. There are things called X-ray Raman and Moss power, which are synchrotron versions of lab-based techniques that you guys know. Okay. So that was my very quick overview of X-rays interacting with matter. Before I roll on and tell you guys about chess, do you guys have questions about anything that you heard so far? There's a lot of key changes in this talk. Okay, let's talk a little bit about chess. So chess, this is home for us, and this is where we're going to be hanging out tomorrow doing experiments at some of these hutches. So chess is one of 5 high-energy synchrotrons in the world, right? So that I told you there are 50, but most of them, when we talk about the energy of the synchrotron, we're talking about the energy of the stored beams. And the higher that energy is, the closer they're traveling to the speed of light, the kind of bigger these things get and more expensive and more elaborate. And so the class of the biggest ones are these high energy rings, and there's 5. So there's 2 in the United States. There's one here. There's one at the Advanced Photon Source. It's Argonne National Lab, which is in Illinois. There are 2 in Europe. One's called the SRF, the other one's called Tetra 3, and then there's one in Japan. It's called Spring 8. So those are the big 5. So chess is one of those where we specialize in what we call hard or high energy X-rays, which are sort of in this 5 to 100 kilovolt range. We're also very proud, and it's a lot of our identity, to be the only synchrotron that exists on a university campus. Well, technically under a university campus, but still sort of right on campus. So we really feel closely tied to the idea of teaching and training. And so that's part of our identity and part of our role in this constellation of 50 synchrotrons. You start, when there's that many, you start to think, well, what's our role? What are we here for? And I think that we believe one of the things we're here for is training people to come into the community. So that's one of our goals. I am going to play a short video that we usually play at the beginning of tours, which sort of gives you a nice overview and animation of the lab and how it works, narrated by our old friend Carl Smolenski. So hopefully you're going to hear Carl's voice in a second, and I can breathe for 2 minutes. This is an overview of chess and how it works.
The accelerator complex creates electron and positron particles and accelerates them to near the speed of light. Initially designed to smash these particles together, it is now finely tuned to generate an intense beam of light that is used to study matter at the atomic scale. This light is called synchrotron radiation. 40 feet below the Cornell campus, positrons are created and pulled into a linear accelerator, or LINAC, where a driving radio frequency is timed to energize and accelerate the particles in a straight line. Once the positrons leave the LINAC, they enter the booster synchrotron, which is similar to the on-ramp of a highway. The positrons travel through radio frequency cavities where they interact with radio waves, getting hurled forward faster and faster until they approach the speed of light. When the positrons reach the desired energy, bunches are transferred into the particle superhighway, the Cornell Electron Storage Ring, CESAR. Electromagnets steer and focus these particles into a circular path, while waves push them like surfers on the ocean. In CESAR, they travel around the half-mile ring at a rate of 400,000 times every second. Special magnets, called undulators, subtly disrupt the path of the positrons as they travel through CESAR. This disruptive process results in the emission of an intense beam of light. The light, in the form of X-rays, is directed down a separate beamline while the positrons continue around the storage ring. Beamlines and experimental stations called hutches make up the research facility called the Cornell High Energy Synchrotron Source, CHESS.
Okay, so that's basically an overview of how chess works. So we are, you can talk about the particle energy in a few ways. So we actually store positrons, as Carl said, and we store them at what we call 6 billion electrons, 6 GeV, which is very, very close to the speed of light. And everything that you see in this sort of schematic, and that you're going to be visiting tomorrow, well, I guess later today, right? Later today. It was built in 2018, so it's a pretty newly upgraded facility, although the lab, in some sense, has been here, since the middle of the last century. Most of the stuff that you're going to see is pretty new. And so we've been running this user facility in its current configuration since 2019. This is sort of the layout of the floor. Right now there are 7 we call beam lines. Each one of these beam lines uses X-rays in different ways for different science missions, different communities, and they're funded by different partners. Of course, that's not something you guys really need to worry about, although it does sort of color the kind of work that they do. So these are sort of the layout of what we have. These guys are existing. This is currently under construction, so you'll see a lot of trucks and earth moving around when we're over there. The existing beam lines, there's sort of 3 chunks of the lab. There's the Center for High Energy X-ray Science, which is run by the National Science Foundation. It's a user facility, so anybody can write a proposal to come in and use these beam lines. There's something we call MAC-CHESS, which is dedicated to macromolecular crystallography at CHESS. So that's really understanding the structure of these large biological molecules. And that's funded by New York State and the National Institute of Health. And so all of these 5 actually, beam lines that exist, these are open to anybody. Anybody can write a proposal and come in and use them. We also have a couple of beam lines that are run by the Department of Defense, the Air Force Research Labs, which you guys are going to see as well. And these, the access is a little bit different. Access is sort of administered by Air Force Research Lab, and they are most interested in sort of giving access to companies that work for them to build aircraft, things like that, or researchers from their labs. But we all sort of collaborate together as one large facility, and many of our scientists and users hop back and forth between different beam lines and programs. Okay, so I've used the word beamline a whole bunch of times, and I haven't told you what they are, what they look like. So for the next little while, I'm going to give you, well, basically for the rest of the talk, I'm going to give you what I call the anatomy of a beamline, just to sort of give you an idea of what these things are that we run for user experiments. So this is an overview of one that's sort of in the front of my mind anyways. This is an example. This is one we're building right now. This will be the new Sector 5. But basically, this gives you an idea of the scale of things. So you have this line of X-rays that's coming straight off a tangent of the ring. And you're going to put a whole bunch of components on the way down. Right here, you start with what we call the white beam. It has a huge amount of power, has as many photons as we can make, many different energies, sort of kilowatt scale amounts of power in a very small beam. So if it hits something and it melts it, we have to do a lot of work to prepare this beam to be exactly what we want at the end when we're going to do our science experiment. And so to give you a sense of size, this whole picture is about 60 meters long, right? So this thing is wider, but not quite as tall as a person, for a sense of scale. We should probably put a person on here. And there's a whole bunch of components. Now, we don't usually look at it this way, like in the way that's sort of blown up, because it's hard to see all the bits and pieces. We tend to draw things like beamline cartoons, so schematically change all the distances and make things bigger so they're easier to see. But this is again sort of a cartoon rundown of something that we're currently building. But it's useful to point out the different bits and pieces of what they do. So the first thing we have to do is make X-rays. In the video that you watched, Carl talked about a set of magnets that wiggles the beam back and forth and uses that to make X-rays. So in this case, we have what we call insertion devices or undulators, which are basically a whole bunch of permanent magnet poles that make a wiggling magnetic field, right? So the beam comes through from the right and passes through these. As it oscillates back and forth, it radiates. That will happen with any time you wiggle a charged particle. It will radiate if you just sort of do it in the normal sense. You get dipole radiation, but because these things are traveling really close to the speed of light, that all gets sort of warped down into this cone in the forward direction. So all what would have been that dipole radiation comes out as a beam pointing straight forwards, which is why we need to get these things going so fast. And then those wiggles, the beams from one electron or positron in a bunch can interfere with other electrons and positrons in a bunch. You can get constructive interference. So this is what we use to make our very bright beams. Here's an example of what these things look like. These are some that are currently being built here at Cornell. This is a CHESS compact undulator. Basically, you have these sort of core pieces, which are magnetic concentrators. You put permanent magnets around them. So you pack a ton of magnetic field into it, and then you build these long arrays of these things side by side, so pointing up, down, up, down, up, down. Put an array on the top, an array on the bottom, you get these very large magnetic fields. And you can tune the strength of those fields by either varying the spacing between them, or varying the phase of those arrays. And if you do that, you can sort of tune the spectrum of flux that you get out of it. So this is sort of a picture of, as a function of energy, how many photons per second you get from different kinds of undulators. And so you can see, on this red curve, for example, you have these very bright harmonics, these spikes, where you get tons of constructive interference and tons of photons. And then, you have areas where you don't get a lot, and you get other spikes at higher energies. It turns out if you then vary the field strength, you can take this guy and you can sweep it along and change the energy where you have all these this bright constructive interference. So you can tune these devices to give you exactly the beam you want. You can change you can build different ones with different periods depending on what spectrum you want. So we do all of that, but this is sort of the first step, right? First we have to make X-rays, and we make them to order as much as we can. So, however, if you want to do an experiment here, you probably want to get rid of this guy and this guy because they're not useful to you. So you want to be able to further isolate just a part of this spectrum for your experiment. So the next thing we do is we have usually what we call crystal optics, monochrometers. Basically, the idea here is we're going to select a specific energy from that spectrum to do our work, right? And so, these are usually, Bragg crystals, or you'll hear a little bit about how diffraction and Bragg diffraction works in a moment, which is the principle that we use to pick energy. But it turns out that basically, if you bring this beam and bounce off of a chunk of perfect silicon a couple of times, only one energy will go through. So the rest of the beam will sort of just pass harmlessly through this first crystal, but the photons that you really want will satisfy this condition of bouncing twice and moving on. Now, this is what these things actually look like in practice. Because the beam has a ton of power in a small spot, we need to keep things from melting. Typically, the way we do that, we sort of come in with this, what we call a double crystal system. So you have two chunks of perfect silicon here that are wedged between copper. And there's another two up here. Each one has a slightly different orientation, so you can do some different energy ranges. And then we flow through these copper tubes. We actually flow liquid nitrogen. So we can keep these chunks of silicon very, very cool, about 100 degrees above absolute zero. It turns out that there's a magic spot for silicon called zero thermal expansion at about 125, where at higher temperatures, it has regular thermal expansion. At lower temperatures, it actually goes backwards. So as you cool it, it expands instead of contracting. But then there's one magic point where it has zero thermal expansion. And if you can manage to get your silicon to sit right there, then it stays very flat, even if you put a ton of energy in it. So typically, we work hard to keep these crystals very cold and very flat so that we get really nice wavefront propagation of the X-rays. We come in, we bounce off this thing twice, and sail on our way. As you change that angle of reflection, you change the energy to the extent. So that's kind of the idea for a monochromator. And this is a sort of a view of all the engineering that goes into each part of this beam line. This thing typically sits in ultraviolet vacuum, so you're coming into some weird-looking tank, high vacuum tank, and then inside you have feeders with all this cryogenics, crystal optics motors to move everything around. The other thing we typically want to do to beams is we want to change their size. So we want, these things are naturally what we call divergent. As they fly farther and farther away from the source, they're slightly spreading out. We want to be able to bring them back together and focus them to the small point that we need, especially if we want to look at very small things with good spatial resolution. So there are several ways to do that. One way that you might do that is with focusing optics or X-ray mirrors. Right? So X-ray mirrors basically work on this principle of total external reflection. So if you come in with an X-ray beam to a very, very perfectly polished flat system, there will be below some angle, you'll get a perfect reflection, the way you usually do with a mirror. But once you get above that critical angle, you don't get any reflection at all. So all X-ray optics are typically glancing angle like this. This is a set that we're designing for a new beam line. It's basically set to work at 1,000th of a radian, right? 1.15 milliradian. So that's like a very small incident angle. It's 0.07 degrees. is the incident angle. And it turns out you can build these systems if you cloak them with high Z elements, they reflect better than low Z elements. So if you coat this thing with platinum, then it will reflect up to 72 kilovolts, which is nice. We like high energies. If you leave them bare silicon, they'll only reflect up to about 27. The reflectance curves kind of look like this. So this is bare silicon. You get reflectivity of 1 means all the photons reflect, and you see sort of, as a function of energy, a really nice flat reflectivity. And then you hit this critical energy around 27, and it just drops like a stone. So as you lower the angle, this line sort of goes up, or as you change the material, it pushes up. So you can do this, and then you can bend and shape these optics to give you kind of focusing. We have other more kind of crazy and wild kinds of optics that we can use as well. I'm not going to go into how they work, but we can do things like polarization control. So we talked a little bit about polarization of the beam and wanting to be able to manipulate it. You can build things that look like this. These are phase plates where basically you bring in a beam that has, say, linear polarization, and then you can manipulate it with X-ray optics to make it helically polarized, circularly left to right. You can manipulate it again and give a new linear polarization that's in a different direction from where you originally started. And the way you typically do this are with very perfect diamond crystals that are set at just right angles so that you can actually manipulate the front of that wave as it passes through this perfect periodic repeating set of atoms inside your chunk of diamonds. So these are kind of fun. We're actually currently building our first set of these for your experiments. But this is the kind of engineering that goes into the beam lines. At the end of the day, as a user, hopefully you just have to press a button that says left circularly polarized light or right circularly polarized light, and that's what you get. But upstream, this is the kind of wild stuff that's going on. Now, at the end of this picture is actually the stuff that we spend the most time thinking about and the stuff that's most relevant to you guys. So from here on up, typically this stuff, as a user, you don't really see or have to worry about too much. Although it does affect your experiment, and it's good to understand how it works. But this stuff tends to be what you see. So things like sample environments and chambers. So if you're going to measure material, typically you also want to control it somehow. In this particular picture, because this is the picture of a high magnetic field beam line, here you have some 20 Tesla magnet. But this could just as easily be a fuel cell that you're trying to understand, or a high pressure cell, or this could be a growth chamber for plants that you're trying to understand. So you have some apparatus that lets you prepare the experiment, or whatever you're trying to learn about. And then you also have a detection system. So you're going to have, after your X-rays interact with your material, or your sample, or your experiment, then you're going to want to collect them. You want to see what happened, what is the signal coming out of your sample. And so these two tend to be the things that happen inside the hutch that you interact the most with as an experimenter. And so for those, we have the widest amount of variability. So I'm not going to go and try to say what all of them are, but I'm just going to quickly, in my last 3 minutes, flash a few pictures of some of these setups that we have at HEXT that you're going to see today and tomorrow. So, it could be that this sample environment is this QM2 beam line. Here we have this whole crazy sample environment that's used to cool samples down to just 3 degrees above absolute zero. So you can make things really, really cold. And then you can rotate them around on 8 different angles to put them in different orientations. There's also this giant detector at the back that collects 6 million different momentum transfers all at the same time. So you can get all of these different measurements of the diffraction for very, very cold samples that are spinning around. And make these sort of big maps in circular space that tell you about where the atoms are. So this is sort of a Fourier transform of all the atoms in this sample at very low temperature. So that's one thing you might do. But it's not the only thing you might do, right? So you can also set up, and this is a picture of Chris and the Pillbox beam line. You guys can see, you can see there's a lot going on in Chris's hutch. But it could be that instead what you're going to do is you're going to put your sample in a flow cell. And in this flow cell, you're going to control the mixing of 2 liquids that are undergoing a chemical reaction. And while that chemical reaction is proceeding, you're going to light that cell up with X-rays and then bounce the emitted X-rays off of some beautiful curved crystal optics into some special detectors that let you see exactly the details of the absorption and the emission process has been going on in the middle of that reaction. So that's something completely different that you might do at the end of your beamline. This is a picture of the fast beamline. In this case, it could be that you have this giant load frame that's set up specifically to tear chunks of metal apart. So you can apply very large tensile or compressive loads to samples, and then you can watch with these beautiful, what we call near-field cameras, you can see all the little polycrystalline grains in the metal, how they deform and squish as you pull that chunk apart. And you can see when cracks start to form. You can watch that happen very, very quickly, right? So a completely different kind of setup in HEXT. But this is one of the reasons why there's 200 beamlines in the country, is because the limit to the kinds of experiments you can do with these X-rays almost doesn't exist, right? It's only limited by your imagination and what you can convince a funding agency to build. The last example I'll give you, this is from our 7A beamline, which I think is pretty cool. You can have a chamber here that allows you to simulate the conditions at sort of the bottom of the ocean in terms of temperature and pressure, where we believe life first evolved. And you can look at actual proteins, macromolecules, in those conditions and try to understand evolutionary questions about the origin of life, the rules of life, and how life evolves at death. Right? And so you have that system, but then, in this case, they also have this giant vacuum chamber. And then at the very end, they have a detector. This is because they do something called small angle scattering. They want to look at the X-rays that change direction the least. So they just get diffracted a little tiny bit out of the straight through beam by the sample. That sounds like an unusual thing to fixate about, but in fact, it has a huge amount of information about really big molecules, which are sort of the building blocks of life. So those are my overviews of a whole beamline and very rapid description of how X-rays interact with matter. I probably raised more questions than I answered, but my time is up, so I'm just going to conclude with where I started. I hope that this helps you guys, this whole 2 days, become sort of informed consumers of other people's X-ray data, and hopefully also convinces you to start thinking about using X-ray facilities in your own research. So we have a lot of great talks coming up. I can probably take some quick questions, but I know I ran over time. But thank you very much. Okay.
All right, I'm just gonna not use the mic. If you don't hear me. Okay, so today I want to talk to you about X-ray scattering and diffraction techniques. But before I dive into what I want to talk about, let me introduce what I am and what I do. So my name is Amlan Das. I am a postdoc at the FAST beamline at CHESS. And I work a lot with metals, so structural metals, and using X-rays to study metals, not only their structure, but also their mechanical properties, thermal properties, dynamics. And I sort of realized today morning that the funny thing about me doing this is, almost 5 years ago, I was basically on the other side of this, as basically one of these chairs, not at this particular workshop, but a different workshop, the same flavor. So this is really cool for me now to be able to do this for you guys. Okay, so as we talk about X-ray scattering, what I first wanted to start off with is how photons interact with matter. Right? So when we talk about X-ray photons, we are talking about a specific, some specific definition of in terms of the energy of these photons. So we are talking about, say, an energy being about somewhat less than keV to somewhat above 100 keV, and this definition is sort of really blurry, but this is sort of the accepted definition of what X-ray photons are. And then there's this other interface between soft and hard X-rays, which again also sometimes gets blurry. But when people talk about soft and hard X-rays, this is basically the regime they're talking about. And we're going to talk about how we use soft and hard X-rays to look at matter, right? So one of the first things I wanted to show, actually, let me see if I can. So one of the first things that I wanted to show is this picture and ask if anybody recognizes this picture or can say anything about this picture.
That's like the first time an X-ray was accidentally taken.
Yes, there. This happens to be one of the first ever medical X-ray taken by Wilhelm Röntgen, I believe late 1800s, and this was basically the first, or Röntgen was the first ever Nobel Prize awarded in 1901, right? So that's sort of the birth of X-rays, and as throughout the course of the last century, you've sort of discovered how they interact with matter in various kind of ways. So we're gonna, take a step back from all of the many photons, the very high brilliance of synchrotron source, and just talk about one photon for a second, and say as one photon is coming in and interacting with matter of whatever kind, there can be various kinds of things that photon is doing. A lot of the times, that photon is just going through, doesn't see any of the matter, which is basically and goes up, transmitted photon. And if it is, however, not being transmitted, or there are chances not being, we actually get to interact with all of these sites, such as an atom, a molecule, an electron, what have you, it can do a variety of things. So the incident photon, which has a wavelength, an energy, a wave vector, can actually elastically scatter off of a site in that the transmitted or the scattered photon has the same energy as the incident photon, so we have elastic scattering or non-scattering. It can inelastically scatter in that it lose some of its energy by transferring momentum to the particles interacting with, which would be Compton scattering. It can knock off electrons sort of in the photoelectric effect, or it can knock off characteristic electrons in the form of Auger electrons, which, by the way, I have learned recently was discovered just prior to Auger discovering this effect by Lisa Meitan. So, probably best called Auger Meitan effect. You can also have this incident photon knock out electrons from shells of atoms, and then other electrons can fill those shells, and we can emit characteristic wavelengths, fluorescence, which you are going to probably hear some later talks. Or you can, have fluorescence of not the parent atom that is you consist of, or inside an impurity. So you can use that to identify the impurity in So we see that X-rays have a variety of different interactions with materials, and we're going to start to look at some of the ones that we can tackle. Well, we have some understanding of all of them, but I chose one of the ones that I think is really cool. I use a lot, which is elastic scattering, and there are a lot of techniques based off elastic scattering. So let's talk about elastic scattering. So for a second, before we dive into how a photon interacts with a wide or big chunk of material, I want to take a second and zoom in and talk about how an electron interacts with, how a photon interacts with, say, one electron or a point scatter, right? So the underlying assumption of the underlying fact behind the elastic scattering is that the incident wave vector and the outgoing wave vectors, the incident photon and the outgoing photon are the same in magnitude, right? Which means they have the same energy, the same wavelength, whatnot. So if you have a photon coming in, you have a scatter which can be an electron oscillating the electron around, and that electron now gives the photon out of the same energy. So the wave vector k coming in, and the wave vector k prime going out, right? So as we try to quantify this, phenomenon, what we do is we consider the number of photons coming in. So there's a number density is proportional to the field or the square field of the wave coming in, or the number of photons coming in proportional to the square of the field of the wave coming in. Here this photon has dual nature, of course. And then from a scattering object, it scatters off basically in every single direction. If you have an electron, it's pretty much uniform scattering in all directions as a wave. But you can look at parts of it, and you can capture how many photons make it through this little solid angle, and you can normalize the number of photons with the solid angle, and basically again normal, which is I scattered over the solid angle, And then you can normalize the whole thing with the number of photons coming in and find out or define what is called a scattering cross-section. Useful in talking about interactions of a photon in pretty much any object, and we can define how that object scatters. This scattering cross-section has units of inverse length squared, so meter squared per centimeter squared inverse, what have you. And alternately, you can define a unit called barns, or people have defined a unit called barns to measure scattering cross-section. And I'm told that this has to do with the phrase of, can you hit the broadside of a barn, scattering, which you should think about how, which is indicative of how rare scattering events are. Okay, so if you have now many electrons in your atom, so if you have, say, a bunch of electrons around in the nucleus of the atom, and you have a bunch of electrons around, you have the same photon coming in and a photon going out, I have defined the angle between the incoming photon and the outgoing photon as theta. We're going to later dive into why we choose this particular definition. And the difference in these two vectors, so if you do k prime minus k, vector difference of these two, you get what you call the scattering vector, which is basically the vector that turns this incoming wave around. Right? So to find out how an atom scatters, so basically consider the electron cloud around the atoms and sum over all of those electron clouds, and that's how we find out how an atom scatters. So that's basically what I'm doing here. I have a density of electrons, and I'm summing over. There's a phase factor that comes in from the position of the electrons and the incoming and the scattering vector, and I'm summing over basically the effect of all of those electrons and finding what is the something called the atomic force factor. This defines how different atoms scatter differently, and if you sort of plot the atomic form factor as a function of the scattering vector, it's just slightly different notation on the x-axis, but you will find that you'll find a couple of different things. You'll find that the scattering probability, or the strength of the scattering goes down at higher and higher angles, right? And what that means is it's easiest for the electron to be scattered very little, and as the angle between the incoming photon and the outgoing photon changes to larger and larger angles, the scattering probability goes down. So that's one thing. The other thing is the atomic form factors found here have elements associated with them, and different elements have different atomic form factors. And the more electrons you have in that element, the more scattering you'll get. So that's the other takeaway. And we don't need to always go and do this integral. You can find tables online, for example. NIST has tables that very nicely have plotted all of these for us, and we can go in and we can look them up. But the main takeaway is that the more electrons you have, the more scattering you have. Which means that high Z elements, or higher atomic number elements, have a lot more scattering than lower atomic number elements.
Can
Yes.
I clarify something before we keep going? I'm trying to understand the concept of scattering. What is scattering?
Sure. Yes. So when we're talking about, in this particular case, when we're talking about elastic scattering, what we're talking about is you have a photon coming in, right? And you have a scatter. It could be an atom, it could be a molecule, it could be an electron, pretty much anything, right? And the photon is interacting with that scatter and sending off another photon in some direction.
Another photon?
Yes.
Another photon?
Yes. So the incoming photon has, for example, an electric field, right? And if you consider this scattered to an electron, that electric field makes this electron sort of vibrate around in space. That makes this electron radiate another electric field, which is basically the outgoing photon.
Okay.
That is, and if the energies of these two photons, the incoming one and the outgoing one, are equal, that's elastic, right? So there's no loss of energies. If, however, these two are not equal, which is inelastic scattering, then that electron now has a little bit of momentum, or the energy difference between the incoming and the output. That's the inelastic scattering. Yes.
So what is the unit measure of scattering? How do you know that okay, we have scattering? What unit is that?
Sorry, you repeat that?
What is the unit measure scattering? The way we measure energy, wavelength. So when scattering has happened, how would you say this information? What measure would you use?
Right. So for example, in this case, you're talking about something like a scattering cross section, which is what I was showing on the slide before, which is sort of, well, if you have a bunch of incoming photons scattering off of this object, there's some distribution. There can be a distribution as to how many scattered photons go out in different directions in space, right? Not all of the incoming photons are going to be scattered at all. Some of them can be dispersed through, but some of them do get scattered in various directions. And as you look at basically the sphere around this object, you can divide up this sphere into sort of very small patches, and through these patches, or through these solid angles, you can have different amounts of photons going through. And you measure basically, you normalize the number of photons going through this patch by the area of this patch or by the solid angle of this patch, and divide that with the incoming number of photons, and that's how you basically understand how many photons are going in which direction. Yes, ma'am, your first.
You mentioned that there was a relationship with the more electrons, the more scattering.
Yes.
So would there be a relationship between the elements and the scattering vector, for example, or is it just a separate phenomenon?
For example, the incoming. So the incoming scattering vector, right, is independent of what you're scattering off of. The incoming scattering vector is how you generated that photon, right? Could be a synchrotron source, could be something else, could be sunlight, right? That has an incoming scattering wave vector. So the incoming wave vector is independent of what you're scattering off. The outgoing wave vector can be elastic depending on how this interaction between incoming and the scatter is inelastic. That's when the scatter starts to be active. Then it's hard to function that.
So for the form factor, is that directly related to the probability of scattering?
The form factor actually is related to the probability of scattering. Basically, you're summing up the scattering from each of these electrons, right? And you're summing them up for all of these electrons in an atom, right? And that's how it's related to the probability of scattering.
Okay, and that rho is like some electron density? Or?
That rho is basically electron density. Yes, you're summing up over the electron density and your and the scattering vector times that probability relationship. Okay. Other questions? Okay. Moving on. So I wanted to do a little bit of recap for you guys. I'm not sure of that of interference patterns, right? So because I find a lot of similarities between, say, something like a Young's Beltway experiment and scattering in that, and I find a lot of similarities. Let me try and convince you that those similarities are actually real. So, so if I have a point source that is radiating in all directions, which is basically what a point scatter or electron is, right? It's radiating in all directions. And if I have a second point source, and now, so you have these two independent point sources, right? And you just expect the waves coming out, and now I'm going to let them interfere, right? So if I have them now both together, you're going to see these alternate patches of constructive and destructive interference that you can, where in certain directions you have constructive interference between these two scatterers, and certain directions of destructive interference you have alternating bright and dark bands, especially. If I move these scatterers around without changing anything else about them, you can see that how these bright and dark patches are sort of shifted around. So basically, it depends on how far away from each other these scatterers are. I can add more, and if I add more, you can again see, if you compare to something like this, or even something like this, you can see that there are some directions in which you have particularly strong constructive interference, and there are some directions in which you don't. And the last thing I'm going to do is I can alter the wavelength of what these things are scattering, and that again affects how or in which directions you can have constructive interference, right? So, a couple things I think that we conclude that matter are how far are your point scatterers from each other? So if you have multiple point scatterers, how far are they from each other? And what are the wavelengths that each of them are scattering off of, which is basically in elastic scattering, it's the incoming wavelength, or the full wavelength of the incoming photon. Why am I talking about this? So, why am I bringing up interference patterns? Because the reason I'm bringing up interference patterns is we've just talked about scattering from an electron and scattering from many electrons in an atom, right? And at some point in materials, you're going to find that you have a row of atoms in each fashion, you also want to be on one, which is not that dissimilar from, say, a row of point scatterers. And the takeaway message I think from here is that if you have many point scatterers, there are certain directions in which they can be constructed. Alright, so what happens if you have a row of atoms? And this, I'm gonna start off by saying that this is a cartoon showing. But say if you have a row of atoms, there's a wave coming in, and that wave hits this particular one atom and turns it into a point scatterer. The other atoms, for example, this one is spaced away from this incoming wave, or this one is spaced quite a bit away from this particular atom, and that is important because by the time the wave reaches the next atom, this atom has already started radiating, as atoms are already started acting as point source, and the radiated wave has reached quite a distance, right? And by the time this second atom becomes a point source of its own, the radiated wave from the first atom has reached a little bit more distance, and so on. So what I'm going to do next is flip this around a little bit, or zoom out and flip this around eventually, and point out that now you have two point scatterers, and between them there's a phase delay. I think when they are active. And this phase delay is important because this phase delay comes from where these two scatterers are located in physical space. And this phase delay impacts where and when they are going to constructively interfere. Right? So in some where the wave fronts align, we have constructive, where they don't align, we have destructive. So in particular directions, you're going to have very intense scattered scattered photons. So you have a photon coming in, just rotating this picture around, the photon coming in from this direction, and in a particular direction, you're going to have a lot of photons scattered, and the other direction, not so much. So the takeaway that I want to highlight here is that for a row of atoms, or for a bunch of atoms that are ordered equally spaced from each other, there are particular directions which are really preferable for scattering, and other directions that are not so preferable. So somebody decided to quantify this, and before we jump into the quantification of which directions are preferable and which are not, let's look at atomic structure for a second, and let's talk about crystals. Crystals are pretty much ubiquitous around us. For example, a lot of metals are actually crystalline in that they have very repeated spacing between atoms. A lot of non-metals are actually also crystalline. For example, I have over here table salt, which is a very common crystalline material. You basically have ceramics that are crystalline. You have a host of materials all around crystalline. And which is good because crystalline materials mean equal space or repeatable spacing between atoms. So we can use our idea of scattering there. Even if you don't have perfect crystallinity or perfect repeatability of positions, you can have something like amorphous metals or glasses, or even silica glasses such as window pane glasses, where you don't have exactly repeatable positions, but you have sort of repeatable positions in that there is some range of positions of if you have find one atom here, the next atom is going to be close by within a small range. And that is also okay. It's not quite as great as crystal in terms of scattering, but it's okay. And then there are polymers where it's a mixture, it can be a mixture of crystallinity and amorphous nature, or more amorphous or more crystalline, or somewhere between the two, which is another story. So, if we talk about how to define a crystal, we basically have a set of points that are either have equal spacing between them, and they are identical, right? So in a lattice, which is basically the underlying basis behind, or the underlying structure behind a crystal, you have a set of points that are equally spaced from each other in this direction, and they are equally spaced from each other in this direction. And those two spacings don't necessarily have to be equal, but they're the same for all as you go along in this direction. Right? And what the point of a lattice is that all of these green points are identical to each other. And that's how a lot of the crystalline materials are built, because now in these green points, I can start to fill them up with whatever I want. You can fill them up with, say, an aluminum atom, you can fill them up with a cat, you can fill them up with a molecule of a protein or something, but the point is that you repeat something in space, whatever you like, and form a crystal. And this, whatever you repeat, what you put in these lattices is called a motif. And if you repeat a motif on a lattice, so lattice plus a motif, a crystal. And a crystal can have characteristic dimensions, which is, in this case, this side of the crystal, for example, has a lattice vector that can be 1 and repeats basically, and the side of the crystal has a different lattice vector, 18, but that also repeats. So somebody came up with the idea of, well, if they repeat, we can only use one of them, to define the entire volume of the crystal, which means we can have one vector defined in real space. And they did some math to come up with a definition of reciprocal lattice vector, which basically under the condition that the real lattice vector, the reciprocal lattice vector, basically multiply them and we end up with a unique matrix. Right? We're going to use this reciprocal lattice vector in a second, because turns out this definition is particularly useful for scattering. This definition of crystal is particularly useful for scattering. So in physically, what reciprocal lattice vectors look like is if you have a real space which is A1 and A2, and these have units of length, you can in reciprocal space have A1 prime and A2 prime units of inverse length and magnitudes of basically 2 pi over whatever the length of the space is. Okay, so why do we use the reciprocal lattice vectors? Well, this Max von Laue, this research was basically done in, I believe, very early 20th century. Could be late 19th century, don't quote me on that. But what he figured out was that there's a particular relationship between the scattering vector, which is the difference between the outgoing and incoming wave vector, and how points are arranged in a lattice. He figured out that there are certain conditions in which you have constructive interference, and certain conditions in which you don't have constructive interference. So he says we don't like these conditions where the scattering vector is not equal to the reciprocal lattice vector. Don't like that because that has constructive interference, but when they do align, you have constructive interference, and it's good. What this means is that there are particular directions in which a photon is scattered from a lattice where you have constructive interference, thus lots of photons. That is basically termed as what are called Laue conditions, and I'm sure you guys are familiar with either this version or the version I'm about to show next, which is Drexler, right? So again, Laue got the Nobel Prize in 1914, I believe, these guys got Nobel Prize in 1915 for these discoveries. What they proposed or what they came up with is a very analogous version of the Laue conditions of constructive and destructive interference from a crystal. They said that if you have a wavelength coming in, particular wavelength of lambda that's coming in, and you're scattering off of a crystal, say off the surface of a crystal, and there's an angle of theta with the incoming wavelength and the surface of the crystal, and there's the outgoing wave has also an angle of theta here. And there is a particular relationship between the d-spacing, or the spacing between these crystallographic planes, and the incoming wavelength, and what particular angle they choose to scatter off of, which is basically what angle you're having constructive interference at, and destructive interference at every other angle. So this is the relationship that I'm sure all of you are familiar with, but this is very analogous to the Laue conditions, except that this is done in real space. So this is done using real measurable quantities such as a wavelength, or lattice spacing, which is units of meters, right? And an angle. The Laue conditions do this in reciprocal space where the math works out probably in a bit meter. So this is basically one particular case of the Laue conditions. All right. So now that we have Bragg's law, and we understand that we have in some cases constructive and some cases destructive interference, we can use this to measure a whole wide variety of interference. If you're doing X-ray diffraction from a crystal, so this is just a metallic crystal or a ceramic crystal, but you have X-ray diffraction, you can have phase stress, phase strain orientation relationships, morticity, crystallinity, a host of different information. You can do, if you have refracting off of, say, lattices made of molecules or, say, a protein crystals, you can have protein crystallography or X-ray crystallography. And then there's a whole variety of techniques where where what you're measuring is not, say, just carrying off individual atoms, but you're measuring the electron density and constructive and destructive interference with electron density in some particular way. So you can have other techniques such as small angle X-ray scattering, wide angle X-ray scattering, very close to the incidence angle scattering, which is gradient incidence scattering, where as compared to, say, small angle scattering, you change the angle of the scatter vector by even lesser amounts. And I believe Jenny is going to talk about some of these things. So anyway, so Bragg's law opens up a whole wide variety of things that we have access to currently. So one of the things that, for example, we've been so far assuming is that the incoming waves have a particular wavelength, and if you so of, say, lambda or what have you, and that has a relationship with the d-spacing between crystallographic planes and the angle that gets scattered off of that. And this allows us to measure something like an intensity to theta plot that I'm sure you're familiar with, where various peaks have various crystallographic directions. However, if you don't have a monochromatic beam, if you, for example, for a second have a polychromatic beam, which is something that you can get at a synchrotron source, you don't use all of the X-ray optics that Jacob was talking about. You can do the same thing, except if you hold it, you don't have to move around in angle. You can hold it at one particular angle and you get a wide variety of diffraction peaks, which basically correspond to different energy or different incoming wavelength at one particular fixed angle. So what my takeaway point from here is that in Bragg's law, which goes as lambda equals 2d sine theta, you can either hold the lambda constant and move around d and sine theta. So all of these have different d spacing and sine theta. Or you can hold the sine theta constant, have your detector at one particular location, and move around in lambda and 2d, same information, right? But suddenly we have now two different ways of using monochromatic and polychromatic radius techniques. So can we extract something other than, say, d-spacing or lattice spacing? Yes, we can. So the reason I chose to mention polychromatic X-rays right there is because we use them not only to look at other materials, but also to enable us to look at other materials. And one particular example that I find really cool, and Jacob touched upon this, is that if you have a synchrotron source that generates not just one particular energy that you are interested in, a particular photon that you're interested in, but a host of other photons, then we gotta find a way of selecting the photon that we want. Right? So what we do is we have a source, and then we put in some what we call a micrometer. And the way a micrometer works is the micrometer holds in this case, for example, a silicon crystal or some other crystal at a particular angle. What this does is it turns a wide variety of photons and only selects one of those and bounces that out at a particular angle. And then you can have another one and just make sure that the path of the beam keeps going in the same direction. Right? So, Bragg's law, I find this particularly cool because not only is it enabling us to, to look at the structure of materials and whatnot, it's also enabling that. So, what I want to mention is basically Bragg's law is enabling Bragg's law at various in conditions such as this, or in various kinds of extra objects. I'm gonna take a second pause here and see if there are any questions.
Earlier they talked about coherence as like a phase thing.
Yes.
How does having, I understand how the monochromator gets the same wavelength, but then how does it also help with coherence?
Help with coherence.
Just because on there it says like temporarily coherent.
Yes. Yes. Thank you for noticing that. Great point. So what it means is that what I mean by temporal coherence is you have the ability of a wave to interfere with itself, right? Because when we were earlier talking about how when you excite one atom with the incoming wave, and then with some delay you excite the next atom, that delay between those two, the time that it takes for the wave to go between those two atoms has to be a reproducible number, otherwise you don't get the same phase delay for every single set of atoms, right? And then you cannot get constructive interference because of the same delay. So what we're doing is, and to have the same delay, you basically want the wavelength to be the same for the entire incoming beam. So you're taking the polyphonic beam and making sure that you're having one particular wavelength. So the delay is the same throughout the pulse of the material. So that's what I mean by temporal.
It's like all of them have the same frequency, not necessarily like they're all lined up.
All of the incoming photons are the same frequency.
Okay.
Okay, I'm running a little bit low on time, so I'm going to speed up a little bit here and very briefly mention that if you don't do XRD or X-ray diffraction at a synchrotron source, you probably use something like this, which is a lab source, which is great, but lab sources typically don't offer the same energies as a high energy synchrotron source. And while that is okay in some cases, what the disadvantage of that is lower energies don't penetrate very far into the material. If you have high energies, you can do something like you can go through the entire bulk of a big sample. And by big, I mean like millimeter size samples you can shoot through, and you can do diffraction from bulk samples as opposed to surface diffraction. Right? So when we are choosing or to do X-ray experiments, it's important to understand what geometry we're choosing, what energy we're choosing, that plays a role into what volume you're getting information from. What other crystallographic information can we extract? So you can extract basically the positions of atoms and how they repeat in space, and you can calculate something called structure factor, which basically takes into account not only their positions in space, which is basically this part, but also the individual atomic form factors for all the atoms. The structure factor takes into account, say, if you're scattering off of an aluminum atom or say gold atom or what have you, and how they are arranged in physical space. And you can measure the structure factor not directly, but basically the intensity that you measure in intensity over theta plot or what have you is square of the not just the structure factor, square of the actual value of the structure factor, and that's what you measure when you do an X-ray diffraction experiment. Such as, for example, this, where if you take the transmitted geometry and if you're doing X-ray diffraction into an area detector, which is something that you're going to see, I believe, at QM2 tomorrow. You can measure an intensity over 2 theta if you just integrate this around this direction. Same as what you measure in that source. Right? If you don't have, the exact same conditions as we get full rings here, if you have, say, a single crystal, you can have very spotty diffraction patterns, which are treated in a different way than, say, if you have full rings. The full rings, if you have, are under the assumption that you have powder diffraction, which is basically a lot of different small crystallites scattering every which way in this direction, but have a particular relationship in this direction, right? So these two things are treated slightly differently, but I just want to introduce that they exist and that you can leverage them not only find information about your underlying crystal structure, but how crystals are oriented in space and all of that. So I'm not going to touch too much upon how crystals are oriented in space, but just briefly mention that if you have these rings on an array detector, or if you have rings on an array detector, or you can have spots on an array detector, and these spots can move around. So if you have large changes in these spots, these are basically different light screens and different d-spacings you're measuring. These spots can rotate around in this direction, and that is indicative of underlying crystallographic orientation. These spots can also move around subtly, so basically in the radial direction here, which is indicative of small changes in the underlying d-spacing. Right? If you have small changes in the lambda equals 2d sin theta, if you have small changes in d, you can have small changes in sin theta. That's something you can probe using these techniques. Alright, so if you don't have single crystals, if you have the powder approximation, you can basically look at how the intensity varies, not only in the radial direction or the 2 theta direction, but also the eta direction, and that is an example of something we call texture. If you're familiar with that, which is how are these underlying crystals preferentially oriented in space. My broad point over here is that monochromatic X-ray diffraction from crystals is an incredibly powerful technique that gives us analysis to not only crystallographic lattice information or phase information, but also orientation and strength. I'm gonna skip over the slide and briefly mention polychromatic diffraction. So we have so far talked about monochromatic diffraction a lot, where you assume going in that you have one particular lambda, right? If you don't have one particular lambda, if you hold it instead the theta constant, you can have a variety of lambdas or a variety of energies. You can extract basically the same information, just replace the 2 theta with an energy on the x-axis, the other information is the same. Why is this of interest? Because now, if we have a polychromatic source, we can leverage a polychromatic source. We don't have to go through all the X-ray optics and whatnot to make it monochromatic and thereby throw away most of the photons, right? If you have an efficient way of generating a lot of photons and variety of energies, you can use that to get some basically red diffraction, but in a slightly different way. And from this, we can tease out information such as lattice strain or lattice orientation. Not orientation, but lattice structure. So the favorite information and strain, and then make, for example, maps of strings such as these, where you look at crystal strings and that come forward. All right. So we have basically 1 minute. And I'm going to end here. I'm going to end here.
Was the mapping on slide 20? I don't know if it was from the orientation from the synchrotron. Oh, was
Yeah.
the other one?
Yeah.
Another. I think it's that. Is that mapping from the synchrotron obtained with the synchrotron?
So this is what I think is an ESD map. So this actually is from a microscope, but the idea is the same, right? You can have, so an ESD gives you orientation between relationship between grains, you can extract the same information from monochromatic X-ray refractions.
So if you compare monochromatic and poly, are you saying poly is better for characterization?
That's a great question, and the answer I think is it depends on what you're looking at, right? It depends on what information you're interested in. Not all information you can get out of polychromatic refraction, and not all information you can get out of monochromatic refraction. You could, it's just different ways of posing the same problem. And one of the good things about polychromatic refraction is that you don't need any of these optics. You don't need a lot of moving parts to move around the angles and whatnot. You can just park the sample at the beam, put it detector somewhere. So in some ways, it's more efficient. But really depends on the problem you're looking at.
Thank you.
Questions? Okay, well, thanks, Aman. Okay, so until then.
Hey everybody. Yeah, so my name is Luisa Sameska. I am a staff scientist at CHESS, and I have the delightful privilege of being the slot in between coffee break and lunch, so I'll try and keep you entertained with lots and lots of imaging. That's what we're trying to do. This is I was just telling Chris, this is like the razzle-dazzle part of synchrotron science because we have lots and lots of pictures, and it's my favorite. I mean, this is the reason that I got interested in synchrotrons in the first place, is all the different things that you can do and all the different kinds of pictures you can make. So my motivation for this talk is trying to convince you that when we say X-ray imaging, that should immediately actually raise questions for you, because X-ray imaging can mean all kinds of different things. These are a huge range of some of the potential things we could talk about when we talk about X-ray imaging. And if I go ahead and kind of identify what these images are for you, it should probably become clear right away that there are huge differences, both in terms of the scale of these images. There's like a supernova on the upper left and an ant head on the upper right. And there's also differences in what information is being conveyed. You should be wondering, what do the different colors mean? What's making the contrast in all of these different images? And so even though all of these images are made possible by X-rays, they can be made in many different ways. And so that's what I'm going to try and unpack for us in this talk. I will also point out that among these examples, the medical X-ray is kind of the only one that would have been possible or maybe really practical in the last couple of decades ago. So there's been huge advances, and this is kind of a rapidly evolving area. So when you see an image formed by X-rays, the questions that I'm going to be encouraging you to think about are the resolution. So what constraints are there? What is setting the size of the image overall, and also the resolution, like how big a pixel is. And then also the contrast. So what information is the color or the dark or bright in the image representing? So the goal of the talk is to just give you information and intuition for a wide range of different answers to these questions for images formed with X-rays. So this is really kind of broad overview. So here's another way of saying that X-ray imaging means a lot of different things, and this time I'm saying it in words instead of in pictures. So it's a little bit wall of text, but this is really just for me to kind of give you a disclaimer that there's lots of different forms of X-ray imaging. I'm not an expert in all of them, not at all. The ones I highlighted here are ones that I personally have experience with and things that I've done here at CHESS. But there's lots and lots more, and there are more of these that even happen at CHESS that I'm not going to talk about in this talk. So there's a lot out there. My goal is really just to give you a sense of, like, a framework for understanding how images can be formed and what they can tell you. So we're covering this really broad range of methods. Is there a really good way to kind of define X-ray imaging that covers this huge range of techniques? For the purposes of our talk, we'll just say, when I'm saying X-ray imaging, I mean a technique that is going to give you a real space 2D image. So a picture of a sample that's not homogeneous, so it has differences somewhere throughout that area. And there are this is also a really good time to note there are lots of reasons that X-rays can be useful. Other speakers this morning have alluded to these. X-rays are penetrating, so they allow you to see inside of a material or with some depth. You don't need to do this experiment in vacuum. You can do experiments that cover a huge range of length scales from interatomic spacings to like macroscopically large objects. There's many different ways to get contrast modes, and we'll talk more about these. There's lots of different sample geometries, and if you do the experiment at a synchrotron, you have the advantage of speed because you have so many X-rays, you can take images fast. So how should we organize this overview? There are lots of different ways we could do it. What I am going to emphasize today are, again, two things. One is the contrast mechanism, so how the data was collected, and then also the kind of the beam size. Is this, are you taking snapshots? Are you getting a 2D image right away? Or do you have to build up the image from pixel by pixel? So I'll unpack both of those things some more throughout this talk. So I want to say a little more about the possible answers to what are the contrast mechanisms and how images are formed. And these questions are really important because they're going to tell you about what you can learn about your sample, kind of what the constraints are, how small a pixel size you can get, how quickly you can take images, what kinds of samples will fit into your experiment, and all of this kinds of thing, how quantitative it is, how sensitive it is. So when I'm talking about contrast mechanisms, this is just another way of organizing the kind of X-ray interactions with matter that Jacob and Amlan also talked about today. This is my way of organizing it. Basically, I like to think about when an X-ray hits at a sample, it can do many different things. There's different probabilities that these things will happen, but it could get absorbed, it can scatter, or if it is absorbed, you can also think about, are you going to see fluorescence from your sample? So those are kind of the three things that I'm talking about today. And we will think about what do those tell you about your sample. So absorption is going to tell you about density contrast. Scattering and diffraction is going to tell you about interatomic spacings or ordering in your sample. And fluorescence and spectroscopy are going to tell you about the chemistry of the sample, what elements are present, what oxidation states, or those kinds of questions. And you'll hear a lot more about the spectroscopy part later in the day. Yeah, so I just said that, sorry. So just kind of overview of what's going on here. Apologies. So we're going to quickly look at full field versus scan probe. Just a quick look at what does that actually mean. So just as an analogy, Google Maps, the full field view is the kind of view from the satellite. Here's all the images, all the image, all at once, kind of big picture looking at your sample. The scan probe idea is kind of like the street view. You have to drive back and forth across the landscape to get an image of what's going on. You're getting one snapshot at a time. In kind of a more schematic view, here's a description that's kind of full field versus scan probe. This is more specific to X-rays. So a full field means you have a big X-ray beam. The sample is fixed, usually, and you're collecting a view of that sample on an area detector. So synchrotron beams are pretty small to begin with, so when I'm saying big, I'm usually thinking about a couple millimeters by a couple millimeters, but just for reference, full field means big beam. The scan probe means you have a small X-ray beam, and the sample is moving. It has to raster through that small focused beam to build up an image point by point. Maybe there's a lens, maybe there's a different kind of focusing optic. And you can get a lot of different contrast mechanisms this way. You could do fluorescence, you could think about scattering, and we'll give you examples of all of these. It's important to note that the time frame is set by whether you're doing full field or scan probe imaging. When you're just taking single snapshots, you can go a lot faster. So the frame rates there are hertz to megahertz on top. But it takes a while to build up an image if you're building it up point by point. So that's minutes to hours to build up one image. Maybe I can just stop there. We good? Okay. So just tying back for a second, this is the list we were looking at earlier, and I've just kind of color coded everything of kind of are these full field or scan probe techniques. So the list contained a mix of those things. And what I want to do next is give you a few examples of experiments for full field and scan probe so you can start to get an idea of what's possible. So here are some of the typical full field setups. On the top, you've got absorption contrast. So this is kind of like your classic medical X-ray. when you're working at a synchrotron, you have the advantage of a more coherent source. So earlier speakers talked about how the X-rays are all kind of in phase with each other. That means that if you put your detector farther away, you can get extra contrast that way. I have some examples to show you of that. And then the last one is showing how lenses can be used for magnification. Say you don't want to just do a direct image of a sample, maybe you want an even smaller spot. Just to give you kind of some examples of how that is typically set up. And so I'm going to show some examples of things, the kinds of things you can do at a synchrotron if you're doing radiography. So I mentioned that you can do fast frame rates. If you've got lots of X-rays, you might as well take really fast movies. So that's the kind of thing that we like to do. This is an example looking at the spray cone of a gasoline fuel injection if you look at that time scale, that's over the course of a millisecond. And what's really neat is that it's showing you not just the shape of the cone overall, as well, you're also seeing structure kind of within that cone. So that's really neat. Talking about movies, this is kind of slightly different time scale, but also relevant. This is looking at a 3D printing nozzle. So you're looking at the very tip of a nozzle that's extruding a mixture of polymer and carbon fibers, and this is printing a kind of a material for structural applications. And one example that's neat about this is the person who was taking these experiments was actually able to capture a clogging event and watch the fibers kind of clog up the nozzle. But the really important part about taking movies like that is that you can actually do things like quantify the fiber alignment as a function of speed through the nozzle and make maps of alignment and make maps of velocity of how the printing is actually working. Because people really want to be able to model these processes so they can make better printed parts. I mentioned phase contrast earlier, so here's an example kind of illustrating that. At the top you see kind of those horizontal lines are meant to be the incoming X-rays, and they're all kind of parallel to each other, and then you can see that the object is sort of disrupting that, and if you put the detector far away enough, you can get positive and negative interference at the edges of the object, and so you get this kind of edge enhancement in your image. So the example on the bottom is showing you the head of an ant, and you get actually increasing contrast as you move the detector further away from the sample. It's a little counterintuitive, but the picture on top is kind of explaining how that's happening. And it's a little bit of an art, kind of placing the detector at the right distance to get the maximal contrast, but it's really neat. It's neat that you can do that, and that you can do that it might seem counterintuitive that you can look at something so light, like an ant head, and still get such excellent contrast with something so penetrating like X-rays. It's one of the advantages, again, of being at a source like a synchrotron. And similarly, this is also a phase contrast example. Work from our beamline where people were looking at water flowing through these nanoscribe fabricated microfluidic devices. So you can see the water kind of go up through those channels and then bead up on top. Just lots of examples. That's what this talk is. Let's see. Here's another couple examples of things you can do with phase contrast on the left. Those are examples of grape buds. So there, I think the beam is actually bigger than that 2 by 2 millimeters that I described, and I believe that was done with something called beam expanding optics, which can make the beam bigger. But that's just so you know that's possible. It is possible to look at slightly bigger things. It's not super common at the beamlines that I'm familiar with, but it's feasible. And then on the right, you're looking at an operating battery, and you're watching the discharge on the left, kind of seeing that profile happen, and on the right, you're watching materials in the battery actually dissolve over time. It's super neat. So one sidebar, so I just showed you mostly kind of time resolved things, so using imaging as a way to get time resolution. Another way people make use of the fast frame rate at the synchrotron is to do tomography, because you can also, again, measure lots of images really fast. So this is kind of the medical version. If you measure a radiograph from many different positions, say around a person, ideally like a 180-degree rotation, you can reconstruct the entire 3D volume. That's the idea, and you're familiar with this from the medical world probably. You have to be able to take a lot of separate images to do this, so it helps to be able to take lots of images quickly. And in the medical version, it's easier to get a person to lie still, and so they rotate the source around the person. But at the synchrotron, the beam is fixed, so the object has to rotate in the X-ray beam. And this is just to give you a sense of kind of the pros and cons of this technique. You can do tomography with absorption or phase contrast, and it gives you, again, 3D distributions or 3D topography inside a whole object without thinning it. So that's a huge advantage if you want to be non-invasive. There are some sample restrictions, though. You need roughly cylindrical objects, and the resolution is limited kind of in relationship to how big your object is. You can't get infinitely small resolution on a really large object. I mean, it's sort of intuitive. Challenges are that samples with low density contrast are really difficult to image. There's an example here of a fossil, but those are really tricky because fossilized bone and fossilized rock don't have a lot of density contrast. That's a useful reason to use a synchrotron because you can do that phase contrast trick and try and get extra edge enhancement. And also, this sort of experiment doesn't give you any chemical information about your sample. It's just giving you kind of density differences. A couple of other examples from chess. There is the grape bud again on the left. So in addition to doing movies, they did some 3D imaging, so you can actually look inside the grape bud. There's a wheat stem on the bottom, and then on the right, those are cementitious materials being compressed. So there's all kinds of things you can do in the kind of material space with these techniques. So everything that we just kind of looked at was this first category of full field imaging. Now I'm going to switch over to talking about scan probe imaging. And this is going to feel maybe a little bit more scattered because there's so many different so many different contrast mechanisms that you can employ here. On the top, we're mostly looking at how dense something is and the differences in that. With scan probe imaging, you can get into a lot more, you have a lot more options for what kind of contrast mechanism you want to use. So here are just some example kind of configurations of how this how a scan probe experiment might be set up. In all of the examples, instead of using a big beam, the beam is focused down to a small spot. And that is what is setting the pixel size in your final image, or at least the minimum pixel size. That and the angle of the beam on the sample. If it's not at 90 degrees, then it's going to spread out on your sample a little bit. The top version is showing a traditional geometry for X-ray fluorescence. Usually you'd mount the detector off to the side to minimize the background from scattering. The second one is it's kind of an example doing diffraction mapping, and the last one is Sachs mapping. And I will say more about all of these in a little bit, but just for that one, maybe notice that I tried to show a schematic with the detector much farther away from the sample. So I'm going to start by talking about X-ray fluorescence. It's an experiment near and dear to my heart, and it's what we'll be playing with in the demo tomorrow, so it's really a fun experiment. But what's going on physically in this experiment, on the left I've got the picture of the atom. So incoming X-ray is actually ionizing some atoms in your sample. When that happens, when you eject a core electron from atoms in your sample, other electrons fall down to fill that hole, and secondary X-rays are emitted. And those secondary X-rays have energies that are precisely specific to the element that was excited. And so those are just kind of showing you two generic possible fingerprints from different elements in the sample. But every atom has its own kind of energy fingerprint. And what we do is measure this fingerprint at every position across a sample, and we extract the peak areas for the different elements at each point. And what you get are these maps. So that's a leaf on the right, showing you the different elemental distributions in that leaf. So the iron is kind of in the vasculature, and the calcium is in the little leaf hairs on a fuzzy leaf, and this is one of my favorite techniques because it has so many applications in so many fields. So now I'm going to overwhelm you with pictures of all the different things you can measure with X-ray fluorescence because it's just so neat. Top left, that is goat horn. So it's a thin section of a goat horn. So horns grow by accumulating rings, kind of like tree rings, and that poor goat was exposed to lead in its lifetime, and so they were studying when a goat is exposed to lead, does the lead stay in just one growth ring, or is it kind of accumulated throughout? And they show that, kind of like a tree, it accumulates in specific dose exposure events. So that was with the State Department of Health, who understandably are interested in what happens when living things are exposed to lead. On the bottom, you have kind of a similar looking sample. That is a fish ear stone. And just kind of like the goat horn and tree ring analogy, those also grow outwards as the fish ages. And in this case, you can find out whether a fish has been in like deep ocean waters or shallow surface waters, how much oxygen was in the water where the fish was swimming based on what trace elements are accumulating in the fish ear over its lifespan. Super neat stuff. It has huge applications in understanding climate change and understanding environmental impact. So on the right, you've got a similar thing. That little blob on the bottom is the fish ear stone, and there they were looking at selenium accumulation in the fish. And they were showing that because you can see the brighter ring is closer to the core, that fish was exposed to selenium earlier in its life, and leading to this kind of spinal deformity that you see. And then on the top, those are beetle wings. Sure, I don't have a nice story with that, but they're neat, right? Some more examples. These are 2 examples from rice. On the upper right, those are rice grains. That's just the copper map, but of course there are maps for every element that you measure at the same time. You don't measure just one element at a time. You can get as many elements as you excite with the incoming X-ray beam. And then the other pictures that I'm showing are from rice leaves. So on the upper left, you can see kind of what the experiment actually looked like in the hutch. We were looking at live rice plants. And you may notice that there are little blotches on those leaves. They're leaves that are infected with a bacteria. So the researchers were trying to understand this disease of rice and how it affects the metals that are moving around in the rice leaf as a result of the bacterial infection. And those are all the different elemental maps along the bottom from those same leaves. And the little inset at the top is just to show you, we can vary the resolution of this experiment depending on kind of how big the spacing of our points is. So on the bottom, we're trying to scan whole leaves, so we were taking relatively large steps. On the top, I can focus the beam down to that's about 5 microns, and so we are looking at a much more microscopic view of the same area, and you can see those bright spots of manganese are associated with the stomata in the leaves, if that means anything to you. It's really neat. This is an example looking at traces of gold in ores. That's kind of the main example on this page. I wanted to show this because it's kind of giving you an example of why would you do this experiment at a synchrotron? Well, this is a needle in a haystack problem. You're looking for these tiny, tiny, tiny trace amounts of gold. You need to be able to measure large areas, and you need to measure them at a relatively quick rate if you want to do anything practical with understanding that. So these are rocks that came directly from a mine. They were just kind of coarsely cross-sectioned and then scanned in the beam line. On the upper right, that is soil from also related to kind of the rice project, looking at arsenic in rice paddy soils. Uptake of arsenic by rice is a really important problem. Changing gears, something else you can do with X-ray fluorescence is study cultural heritage objects. I know at least a couple of my colleagues have mentioned that, and that's one of the things that I was super excited about when I came to work at the Synchrotron. So this is an example looking at a historical photograph. It's called a daguerreotype. So it was a print that was made on a silver plate. And you may know silver tarnishes. So you can see the image on the left looks really terrible. You can't really see a whole lot of the original photograph. But with the synchrotron, we can do X-ray fluorescence mapping, and we can actually see the mercury and gold particles that were used to form the image, because the image is made up of actually mercury-silver amalgam. And so we can recover the image completely non-invasively without doing any kind of cleaning, because these are really, really fragile objects. It was super exciting. This example is just, again, also dear to my heart. This was the very first experiment I did at CHEXT, just studying this painting. It was bonkers. This is a 17th century Dutch painting, and on the left you can see, looks like just a cat sitting on a windowsill. But because X-rays are penetrating, you can see information about the layers that are underneath that surface painting. So in the middle you have the map of lead. You can see that there was originally a girl in the composition. And in the iron map, you can actually see like shadows that were left, kind of spaces that were left when the artist painted in the background. And there's a shadow of a person, looks like an artist sitting in an easel in a globe. So there were at least like two completely different scenes going on in this picture before. I guess the artist just decided they liked the cat best, put a curtain, end of the day. It's really, you can get incredibly detailed and beautiful images from this method. It's one of my favorites. if you, so the second scan probe measurement I mentioned fluorescence, I also mentioned diffraction, so which you've also heard about already today. I won't go into too much detail about this since you already heard a lot about it this morning, but this is an example of doing both fluorescence and diffraction at the same time. So this was kind of an interesting geometry that's at the top where we put the sample, which was this parchment fragment, and we were able to use kind of a special X-ray fluorescence detector that didn't have to be off to the side. It could be placed sort of in line with the beam. And then we could put an area detector in the back, and so you can get both the chemical information and the kind of interatomic spacing information at the same time. And that lets you do things like, if you measure, for example, that lead map, there's actually more than one lead-rich pigment, and so the diffraction lets you split apart, well, those are two different lead pigments. And similar for the copper, you can see that the copper is actually made up of malachite and azurite, not just one pigment, but two. So the elements alone can't identify the minerals. When you have these two different pieces of information, it lets you make much more specific identifications. So this is cool. Interesting that was animated. Apologies for that. This is just one other example of doing simultaneous fluorescence and diffraction that was a little bit more recent, kind of an environmental application. I have a colleague on campus who's studying wood chip bioreactors, which are these kind of like pits in the ground where water can flow through and potentially kind of absorb and take up nitrogen from water and reduce the amount of runoff from agricultural lands. This is a really important problem. But the limiting factor is how much carbon is available to react. And so they really want to better understand how the wood chips in these reactors are breaking down. And so on the left, they're looking at the distribution of metals, iron, manganese, and calcium. And on the right, they're looking at the crystallinity of the wood chip and trying to understand the relationship between where those metal centers are reactive and where things are breaking down faster or slower. Really neat. So I couldn't pass up the chance to talk about scanning probe diffraction without showing this example. Even though it's not exactly imaging, I'm going to get away with it because it's really neat. So this is a composite of synchronized movies showing an in situ laser annealing experiment at our beamline. I guess what you can see on the top is a wafer, kind of top right, maybe you can see that circular wafer, and it has different elements scattered across it. And there's also a laser that can anneal that wafer in different positions. And so the position on the wafer and the laser kind of heat and exposure time lead to different crystalline phases on the wafer. And so we're measuring X-ray diffraction. So they'll anneal, and then they'll scan it through the beam. That's what you're seeing on the bottom with a tiny focus probe. We're kind of crossing over that annealed area and seeing how the material phases are changing. The picture on the bottom right is the actual diffraction pattern that matches. So let's see. Anneal has happened, and now we're scanning across that fully annealed area. You can see the diffraction pattern changing as a function of position. So not an imaging, but it's line scanning. It's neat. This is a really cool experiment because this group has been working hard on making this an autonomous measurement that can actually run at the synchrotron from across their lab on campus, completely independently. Super neat. I also said I would mention scanning probe SACs, so I do have one example of that. This is a diffraction measurement where the detector is, again, like much farther away from the sample. So instead of telling you about interatomic spacing, which is like what the diffraction or wax was telling you about, so not crystalline phases, this is telling you more about larger length scales. Again, from kind of the Bragg's law that we were talking about, if you have smaller angles, that translates to a larger D that you're measuring. So these are bigger spacings, longer range ordering. So when you collect a series of SACS patterns, you've got, what this means is you've got a 2D detector image for every point that you measured in your sample. And you need to figure out which parts of that image are actually useful. So for this example, this is another 3D printing experiment where they're looking at epoxy, a nanoclay, and some carbon fibers. And it turns out the thing that's really showing up in the SACS is the orientation of these nanoclay platelets. When they're edge onto the X-ray beam, they cause really intense scattering in the SACS. And so the real data that we're measuring is kind of what's shown in the upper right. It's basically just a blob of intensity, and the orientation of the blob is telling you about how the nanoclay is oriented in the sample. The reason that's neat is that you can get maps of a cross-section of this 3D printed material, and you can see how the nanoclay is oriented. It's so there's the extent of orientation, which is kind of the blue map, and then the one that's colorful with red and green, that's showing both the angle and the extent of orientation. So where it's kind of white, that means there's less orientation overall. And then the colors are telling you, not only is it more oriented in those positions, the colors are telling you the direction of orientation. Basically, the nanoclay is ordered as it's extruded out of the nozzle and as the nozzle is kind of run past it as it does subsequent rows. It's really kind of as the schematic is showing you. Also, another kind of side note, to wrap up the scanning probe section, I just want to add what we talked about 2D and 3D in the full field version. What about 3D in the scan probe world? For X-ray fluorescence, one approach that people use is confocal XRF. So in the usual experiment, the incoming beam goes into the sample and it excites the material at all these different depths. You can see how that blue incident X-ray is going right through the sample. It's a penetrating radiation. If you put an optic on your detector, then you can actually limit what signal you're collecting to a specific depth in the sample. And so what this lets you do is measure virtual slices in the sample without actually physically thinning your sample. So that's, that example is showing you a flower bud. So there has been a thick section cut of it, but rather than trying to make a section that's 5 microns thick, you can actually do that virtually with a confocal measurement. And you can do that as a subsurface measurement, which is kind of what's in the middle and on the top right. You can also do that as kind of like a virtual depth section into the sample by changing the sample detector distance. And that's what's on the bottom right. Really cool stuff. So those little bright dots are actually individual pollen grains in the sample. And just to kind of put that in context with the larger area mapping, on the top, those are flower buds, different genotypes, and you can see that they accumulate metals differently. On the bottom, so that's like a 40 micron spot size that took about 2 hours to collect, just to give you a sense of scale. The confocal measurement on the bottom has a much smaller spot size, it's many more pixels, and even though the time per pixel is about the same, and this actually took more like 8 hours because it's so many more pixels. I also want to say a little bit about computed tomography. So we talked about this in the context of full field imaging, but in reality, any series of 2D images that you collect at different angles can be reconstructed into a 3D image. And so you can do XRF tomography and get 3D elemental maps that way, or you could do SAX tomography. These are just a couple of examples. The downside is that 2D image formation, because it's a scan probe measurement, is much, much slower than full field imaging. So it's really slow to collect this kind of data. That seed on the lower left probably took something like 12 or 14 hours. And this also means there's sample size limitations. It would just take too long to do for really large objects. And there's also beam damage limitations if you're scanning a sample over and over again at all of these different angles, and then that's also a limiting potential factor. You're going to hear a lot more about spectroscopy later today, so I don't want to steal your thunder, Chris. But I do want to mention that spectroscopy can also be a scan probe technique. If you measure X-ray fluorescent maps with different incident energies, you can get information about the element's oxidation state and coordination chemistry. So both of these examples happen to be with arsenic. The top one is a dried baby shrimp, and the bottom one is a rock. But the idea is that you've taken these maps at different energies, and you can then extract the absorption spectrum from any individual point in that stack of elemental maps. This is also a long experiment because you're taking 2D maps with rastering over the sample many, many times. So the total number of scan times increases with the energy resolution you're trying to get. If you're just trying to get kind of is it this oxidation state or that oxidation state, maybe you don't need as many maps to make that distinction, but if you're trying to make really subtle distinctions in coordination chemistry, then it would take a lot longer, I think. I haven't done lots of this, but it is really neat. Right, so wrapping up full field versus scan probe. This is a useful definition because it helps you know what contrast mechanisms are possible, what is the spatial resolution, like what is determining the spatial resolution? Is it the detector pixels in full field, or is it the size of how small you can focus your beam? It tells you how fast you can acquire an image. Are you just framing as quickly as the camera can frame, or is it how long do you sit at each pixel and how many pixels are there? And it also, from like a scientist's perspective, tells you how you need to optimize your beam line, what energies are needed, what kind of focusing is needed, all those optics questions, and kind of how the optics and detectors are going to improve your imaging experiment. And it helps you also understand what's possible with X-rays versus what's possible with other forms of microscopy, like optical microscopy, fluorescence, like looking at tagged proteins and things like that. So it just helps you, hopefully it will help you choose what's best for your sample. So the provocative question, we talked about these distinctions, full field and scan probe. Can you do both at once? I'm not going to go into all the lengthy answers, but at our beamline we try and do both. We do we have the ability to do mode switching anyway, so not both at once. So if you're visiting us during the demo, then you'll see the functional materials beamline is made to be kind of modular. So the middle table, when you're looking at those optical tables, is the sample environment. On the right is the upstream optics, and that's where we choose. Do we want a big beam, a couple of millimeters by a couple of millimeters, or do we want to focus down to just a few microns? And then on the left, those are where the detectors sit, and we can choose whether we want to do full field imaging with a camera there, or with our scattering detectors, where we can measure SACs and wax at the same time. Just to kind of give you a sense of how those different experiment configurations might translate into the beamline. I think that's everything I wanted to talk about today.
My name is Chris Holly. I'm a staff scientist here at JET, and my expertise is in X-ray spectroscopy. And hopefully, over the course of the next 45 minutes or so, I'll tell you a little bit about what spectroscopy is and how X-ray spectroscopy can help you all do your research. So, I like to think of, we do these really complicated methods because we have specific questions that we want to answer as scientists. And so when I think about different spectroscopic methods that we can apply to various systems, the kinds of questions that we often find ourselves asking are things like, what is the 3D structure of my compound or my material? What is the electronic structure of that material? Not where are the atoms, where are the electrons? Is my compound pure, or is it a mixture of different species? What cool things can this material do? Does it do reactions? Does it have interesting electronic properties? What makes it special? And how can I improve the special properties that this has? And so hopefully, by the end of this talk, you'll see that X-ray spectroscopy can help us answer some of these questions that you all might have about the systems that you're studying in grad school. Okay, so I'll lead with probably the most important slide in this talk, which is, what is X-ray spectroscopy and how can it help you? Well, as you've heard a couple times at this point today, hard X-rays are inherently element selective, and what that means is that even if you have a very complex system, let's say you have a protein that has one iron atom and 50,000 carbons in it, and you don't know what the iron is doing. Well, with X-ray spectroscopy, you can zoom in and you can look at just that iron and ignore all of the carbon cabbage around. The same thing with, you have like a battery, and a battery has manganese and coal and nickel in it, and you only want to look at the cobalt. You can absolutely do that. You can ignore all the other metals and just look at one. So these are very powerful, specific techniques. They're also bulk sensitive. It can be applied to a wide variety of sample quantities. So if you have a fuel cell, or you have a battery, or you have an enzyme in solution, or you have a compound that only has interesting properties at 10 Kelvin, you can look at all of these things with X-ray spectroscopy. So it's a very widely applicable technique. Data collection can be very fast. Depending on the beamline you're at and the instrumentation we have, we can collect data down to milliseconds or even faster. So if you want to know how a chemical reaction is going, and it happens very quickly, we can also answer those questions. The most important thing that we can do, though, is that these methods allow us access to my... Okay, thank you. These methods allow us access to unique information that can be difficult or impossible to obtain with other methods. And that's really the big reason you would do spectroscopy and come to a facility like CHESS, because this is the best way to get out the information that you want to get. Okay. So we'll talk about three main techniques here today. So we'll start out with an introduction, This will cover a lot of ground you've already covered today, which is good. Repetition is a good thing. Then we'll start out by looking at X-ray absorption spectroscopy. We'll then move on to X-ray emission spectroscopy. And then at the end, if we have time, we'll talk about the cool things you can do when you combine those methods together to get two-dimensional type techniques. Okay, so you have seen this slide before in various forms. This is the electromagnetic spectrum. And this is just to highlight the fact that when we do X-ray spectroscopy, we're highlighting this area up here at very high energies. So if any of you have ever done a UV vis spectrum in the general chemistry lab, you were looking at visible light down here that has energies of 1 to 5 electron volts. When we do X-ray spectroscopy, we're looking in the thousands of electron volts. So these are very high energy techniques. For the chemists in the room, 1 EV is about 23 kcals per mole, and we're at thousands of EV. So super, super high energies. High enough energies that we're exciting core level electrons on atoms. So when you do UV vis, you're looking at valence electrons. When we do X-ray spectroscopy, we're looking at core level electrons. And that gives us some of the useful features of X-ray spectroscopy because we're down at those super high energies. You've also seen this slide multiple times today, which is what does an X-ray do when it interacts with the sample? Well, the simple thing you can do is just go through the sample. You can be transmitted. You can use that to collect some X-ray spectra. Look at the beam that comes through the sample. You can also have elastic scattering. As spectroscopists, we tend to try to reduce the elastic scattering, so we tend not to like that one very much. You can also have inelastic scattering. We also tend not to really like that one too much either. You can also have absorption and fluorescence, so the sample can absorb that X-ray and then give off X-rays of a different energy. We do like that because we can do spectroscopy with that. So for us, we mainly looked at what goes through the beam and what do we emit after the sample is excited by an X-ray. So by training, I'm a chemist, so I think of things in terms of orbitals. Apologies in advance if you don't think in terms of orbitals. I'll try to minimize these pictures. But basically, if we think about the electronic structure of an atom or a material, you have a set of filled orbitals, kind of in an imaginary line, and then some unoccupied orbitals, and then what you can think of as the continuum, or just unbound electrons. So for X-ray absorption, what we do is we come in and we hit our atom with a high energy X-ray photon. High enough energy that we can excite these core level electrons into the unoccupied orbitals or up into the continuum. So basically, we can't send an electron to where they already exist, but we can send it to anywhere that's open. So XAS is the absorption of an X-ray photon. The other side of things, X-ray emission, as you might be able to guess from the name, was looking at photons that get emitted from a sample. So in XAS, at the end of that, you end up with a hole in a core orbital. And as you might be able to imagine, this is not a very happy state for this atom. This is a very angry atom. It doesn't like to have that high energy state there. So within a femtosecond or so, what happens is electrons from higher lying orbitals will decay. Whoa, boy, that was almost a femtosecond too. Okay. So within a femtosecond, you'll have an electron from a higher lying filled orbital decay to fill that hole. When that happens, something that can happen is you can give off a fluorescent X-ray photon. That's what we measure in X-ray emission spectroscopy. So two halves of this are what gets absorbed and what gets emitted after that absorption event. So we've said that these are element selective techniques. So what I'm plotting here is the energy of those absorption events versus the atomic number for both the 1s and the 2p electrons. What you can see is as the atomic number goes up, you're always increasing in energy. And so starting out just a couple EV, all the way up to 100,000 EV, very high atomic numbers. You'll see that the 1s is always requires more energy than the 2p, because the 1s is lower in energy, requires more higher X-ray photon energy to be ejected from that atom. And what you'll see if you zoom in this area from 4 to 16 keV, is these dots are actually fairly well separated. Each element is separated from its neighbors by a couple of hundred EV. And that's what gives us the element selectivity of these methods, because the resolution of our incident X-rays can be from about half an EV to about 5 EV at our beam lines. That's definitely high enough resolution to be able to distinguish the different atoms. So this is where the element selectivity comes from. This range is actually the energy range that my beam line usually covers here at CHESS. So what you can see is that even over this relatively small range, we can hit many different atoms. If we look more broadly, the whole range that I can get to is about 4 to 58 keV. And so what that enables us to do is we can hit calcium all the way on up to uranium and elements that we don't get to work at because we don't work at Los Alamos. So almost the entire periodic table is accessible to us. There are other beamlines in the world that can get down to these even lower elements, down to like carbon and nitrogen. Those become very challenging experiments. We don't do these here at CHESS, but we can still hit most of the periodic table. So almost regardless of what you're interested in, we can probably help you out with spectroscopy. So what can we do? Well, we've been saying that at these high energies, X-rays have relatively long penetration depths into samples. So what that means is that we can look at a variety of different sample environments. Here's just a couple of examples. Here we have just a solid powder sitting in a plate. That little spot there is actually where the X-ray has hit the sample. So some discoloration, some beam damage, because this can be a destructive technique sometimes. We've also looked at electrochemical cells, so samples under applied potential. We've looked at thin films, and we looked at solutions, flowing solutions that are actively being mixed. And this is good for biological samples. And just about everything in between. This is only a small subset of the kinds of things we've measured. So spectroscopy can be a very versatile, very widely applicable technique. Probably the most fun part about X-ray spectroscopy is most of it is done at synchrotron facilities. You need relatively high intensities, and you also need generally to have energy tunable X-rays. So lab sources tend not to provide these qualities, as much as synchrotrons do. So almost all spectroscopy is done at these facilities. I'm showing my favorite one here in the middle. There's also SSRL out in California, Spring 8 in Japan, and ESRF in France. So not only do we do cool methods, but we can sometimes get to travel to cool places to collect data. So that's kind of an added bonus of doing synchrotron methods. So another very important slide here. So we have talked a lot today about different methods you can do, but not all beamlines can do all methods. And so if you have an experiment that you might want to think about doing, Google is your friend. So if you want to find a beamline that can possibly do that, just about every synchrotron in the world has pages like this for their beamlines. I stole this one from the Stanford synchrotron light source. And so basically what these kinds of pages show you is they show you what techniques the beamline can do, things like the energy curve. Stop, what am I doing? I'm so spastic today. What the energy range is, what the resolution is, the different equipment the beamlines have, and the different techniques they can do. So if you have a question about can you do an experiment someplace, first Google it, and the most important piece I didn't highlight is the contact information at the bottom. Every beamline will have scientists in charge of it, and we like hearing from potential users. So if you have questions about experiments, don't hesitate to reach out to us. We like hearing from users. So please don't be shy. Okay, so that was a short little intro. I'm going to pause here for questions. Any questions about any of these slides you've seen a couple times before? Nothing, okay. We're going to jump into X-ray absorption spectroscopy then. So, as a cartoon of what an XAS experiment looks like, we start by making our X-rays in big expensive ring. First thing we do is we measure the intensity of those X-rays before they hit the sample. Because we're scanning in energy, the intensity of the X-rays will change as you change energy, so we want to know exactly what the intensity is at each energy before it hits your sample. We then have your sample, it can be any of those things we showed you on the other slide, and then we can measure the XAS in a couple of different ways. The simplest is to just measure the intensity after the sample. So this is like a UV-Vis experiment, but with X-rays. That's good for very concentrated samples that are not too thick, but not too thin. Things that have basically fairly strong signal. For samples that you can't get the X-rays through, or that might have relatively weak signal, you can also measure data in fluorescence mode. So you basically have a solid state detector out here at 90 degrees. And whenever your sample is absorbing X-rays, we saw on the previous slide, that it will also be fluorescing. And so you collect that fluorescence as a proxy measurement for the absorption and measure XAS that way. Okay. See this cartoon again. XAS, absorb that photon, excites the electron into these unoccupied orbitals or completely ionizes it, and that gives us a spectrum that looks something like this. So what this is we have three main areas of this spectrum that are interesting to us. The first is what we call a pre-edge, then we have an edge, and then we have what we call the x-axis. So the pre-edge is excitations of this 1s electron into bound orbitals. So if we're looking at transition metals, this would be something like 1s to 3d transitions. So bound, well-defined final states. If we go a little bit higher in energy, we've now given this electron enough energy to completely ionize out of that atom. So it's taking this electron, sending it up into the continuum. That's what this intense edge step is. If you give the electron even more energy, you get these little wiggles that come after the edge that we call XFs. And I'll go through each one of these different regions of the spectrum and tell you what information we can get out of each one of these that might be of interest to you. So, looking at the edges. Here I'm showing you a series of spectra for manganese 2, manganese 3, and manganese 4. What you'll notice is that as you increase the manganese oxidation state, the energy of that edge marches from low energy to higher to higher. So the edges can be a fingerprint for the oxidation state of an atom in a sample. Now, so where does this come from? Well, if we come back to our nice friendly orbital picture, we say this is manganese 2. The edge is, again, ionizing this 1s electron to the continuum. Well, if you oxidize the manganese from manganese 2 to manganese 3, what you've done is you've removed an electron from that manganese atom. So that means that that nucleus, which still has 25 protons in it, holds on to all of the remaining electrons a little bit tighter. And so what that means is that the energy of that 1s drops down. It becomes more stable. It's being held onto more tightly by that nucleus. So it takes more energy to excite this 1s electron to the continuum, and the edge moves a little bit up in energy. Even more so for manganese 4. Drop down even more energy, you need even more to ionize, so the edge continues to shift. So the edges can be a great fingerprint method for looking at the oxidation state of the atom in your sample. This has seen a lot of use for things like electrochemistry. So if you have a sample, like this one here, they had cobalt and manganese in an oxide environment, they were applying different potentials, they saw a neat reactivity happen, but they didn't know which one of these atoms was actually involved in doing the chemistry. So they did XIS at both the cobalt and the manganese edge, making use of this element selectivity of these methods, and what they saw is that when they looked at the manganese, as they changed potential, they saw this edge shift to lower and lower energy. So the manganese was becoming more reduced as they applied different potentials to this sample. So that was a very cool result, and together with other evidence, they could piece together what the reaction cycle was in this system that they had. So that was edges in a nutshell. If we look down at those pre-edges now, see that they're a lot less intense than the edges. So there are these tiny little transitions before we get to the main edge. In transition metals, or in first-row transition metals, these are 1s to 3d transitions. And so what we're seeing here is a series of compounds that go from iron 4 to iron 5 to iron 6. And you see that much like the edges, as you go to higher oxidation state, you move to higher and higher energy. The reason the pre-edges do that is exactly the same as the edges. The 3D orbitals are affected less by that increased nuclear potential than 1s, so you need more and more energy to excite into the 3D orbitals. You'll also notice that you get more and more intense as you go up in iron oxidation state. The simplest reason for that is as you go from iron 4 to 5 to 6, you go from being D4 to D3 to D2. So you have more holes in the D manifold, more places to send that electron from the 1s, higher probability, so more intensity. So again, this is a measure of the oxidation state of the absorbing atom. And if that's all there were to it, pre-edges would just be basically edges but small. But they're not, they're more than that. Because what you see here is, here I'm showing you two manganese 5 compounds that have very different pre-edges, both in energy and in intensity. And the reason for that is because not only do pre-edges give you information about oxidation state, but also about absorbing atom symmetry. So I won't go into the quantum mechanics behind this. I actually don't have any math in this talk whatsoever, so you're welcome for that. But because of quantum mechanics, on atoms that are centrosymmetric, so atoms that are symmetric across themselves, pre-edges are formally forbidden in quantum mechanics, so you get very low intensity. When you break that centrosymmetry, your pre-edge can gain intensity. And so here we have, in red, we have a manganese that only has 5 atoms bonded to it, and in blue we have one that has 6. So the 6th one is closer to centrosymmetric. It has less pre-edge intensity than the one that is less centrosymmetric. It has more pre-edge intensity. So this is a very dramatic change, losing an entire ligand. But even relatively small perturbations can be seen in pre-edges. So if you're interested in what is the precise geometry around an absorbing atom, pre-edges can be very helpful for that. Over here on the right, this is just a series of iron chlorides that are either tetrahedral, these two, or octahedral. And you can see when you're octahedral, that is centrosymmetric. So you have these very low, very sad-looking pre-edges. Whereas when you go to tetrahedral, that is very much not centrosymmetric, and you get these beautiful, nice, high-intensity pre-edges. So site symmetry, site geometry, you can read off from this pre-edge intensity. And now, just to give you an idea of how sensitive this can be, here is an example of a couple of manganese dimers that are bridged either by 2 oxygens, an oxo-hydroxo, or 2 hydroxides. And protons can be pretty hard to find in chemical systems. They're small, they tend to jump around. You can't see them in things like crystallography or even XFs. But here with these pre-edges, what we can see is that as you add protons to this core, you lose pre-edge intensity because this becomes more and more symmetric as you add protons. So even though this is a relatively small structural change, we can see it from the pre-edge. So pre-edges can be quite sensitive to even subtle structural perturbations. Okay, so that was pre-edges and edges. We're going to move on to the XFs now. And you could be forgiven for thinking that XFs shouldn't exist because, like I said, this is the region where we have fully ionized an electron off the atom, and we're just giving it more and more energy. So why does it have wiggles? It really shouldn't have wiggles. It should just be flat. Well, the reason it has wiggles is because that electron that's being ionized propagates out as a wave. Wave-particle duality and all that. And as it propagates out as a wave, it can interfere and scatter. It can scatter off the electrons of nearby atoms and get scattered back toward itself. So it can actually interfere with itself. And that's what gives you these maxima and minima. Constructive interference gives you maxima, destructive gives you minima, and you get these wiggles. Now, there's a lot of math involved in this. Again, I'm not going to show you any of that math, only the important things, which is from those wiggles, we can learn things like the distance of the scattering atoms from the absorber, how many there are, and their identities. And now this might not sound very special because you can get the same information often with much better precision from things like crystallography, but with XFs, you don't need a crystal. This can be an amorphous solid, this can be in a liquid, this can be as disordered as you can come up with. You can still do XFs on it, and you can get this information out. So if you have a crystal, please do crystallography. If you don't have a crystal, come do XFs. So when you extract the XFs, you might see XFs in the paper reporter looking like something like this. And I don't know about you all, but I look at this and I see a bunch of wiggles, and that doesn't mean a whole lot to me. So what people do is they take the Fourier transform of these wiggles. And what that does is that converts this from inverse distance space into what you can think of as real space plus a phase shift. And so from these Fourier transforms, what you're at, I need to learn how to use a pointer, man. Okay. So what you can think of this as reporting as scattering intensity versus distance. So you see that we have 2 shells relatively close together, and then something else going on at longer distance. So this can be used, again, this is an example using manganese. I clearly like manganese. This is also an electrochemical example, but basically what they could see is at different potentials, they could look at how the different manganese interactions changed on these absorbing sites. So you see that you have manganese in its first shell, giving you a nice intense peak here. At certain potentials, you also have manganese interactions at longer distance. And at this green one, at highest potential, you even have very long range interactions that you can see. So you can get local structural information from non-crystalline samples using XFs. This can be useful for something like biology. So here's an enzyme that starts out as manganese 2 iron 2, reacts with oxygen to give you manganese 4 iron 4, and then does some chemistry to become manganese 4 iron 3. And there are questions about what do these different states look like. This one you can crystallize, so that's great, you can find out what that looks like. But these other two are very short-lived. You cannot crystallize them. And you still want to know what those look like to understand that reaction, so you can take XFs. Again, you can use the element selectivity. You can look at the manganese and the iron independently. So you can see this is what iron looks like, this is what manganese looks like, and you can figure out what these different intermediate structures are even though you can't crystallize these types of samples. So super useful for figuring out reaction mechanisms in complicated systems. For the more catalytically oriented of us, you can also do this on solid state systems. So for these authors, they had what you can think of as a capillary, and they flowed reactants along this capillary, and if you look at different points along the capillary, you look at different reaction intermediates. So you capture different things depending on what point along that capillary you look. They did both XAS and XFs, and they could see both oxidation state changes and also the bond distance changes during the course of this reaction. So they could use this to piece together how their catalyst was working at different stages of that reaction. So this is just a cheat sheet. These slides will all be online, so if you don't want to listen to me talk for 45 minutes, you can just look at these cheat sheets and you have all the information I'm telling you. So I'll pause here and ask for any questions about XAS while I take a drink. Any questions? Nothing. Explaining it that well.
Yep.
Cool. Okay. So move on to XES. So again, we'll start with one of these cartoons. See, XES looks a little bit different than the XAS experiment. So we still hit the sample with some incident high energy X-rays, but now we don't care what happens after the sample. We don't care about that absorption event. We care about the signal coming off the sample. And so to measure those emitted photons, we use what we call a crystal array spectrometer, which is basically a series of perfect crystals that will capture some of that X-ray fluorescence, do energy selection based on Bragg diffraction, and send only a single energy down to a detector. Now, from Bragg's law that Amlan was telling us about earlier, you can change the energy that we detect by changing the angle of these analyzers relative to the sample. So you basically scan the detector and these crystals along these circles that I have drawn in, and by scanning that, you can scan an entire spectrum to get the X-ray emission spectrum. So again, I like these cartoons. So that was basically the XAS part of this. You kick out an electron from an absorbing atom, leaving this hole. And for X-ray emission, what we do is we wait a little bit longer, and we see the events that happen to come and fill that hole. For a first row transition metal, there are a couple of different things that can happen. So these are named up here. You can tell that physicists named these because chemists would never give things crazy names like this. But basically, there's three possible things that can happen. They're called the K-alpha emission, K-beta emission, and what we call the valenced core emission. And I'll talk about each one of these now. So for these transition metals, the K-alpha is a 2p to 1s transition. These are nice because they tend to be very intense, they're very easy to see, but unfortunately the metal 2p orbitals don't really involve themselves in bonding very much. So there's not a whole lot of chemically useful information. They tend not to change compound to compound. So we spend less time looking at K-alpha. K-beta are 3p to 1s transitions. And now the 3p also are not directly involved in bonding, but they're close enough to the valence that they can talk to the valence electrons. So these actually do have some chemically useful information about like spin and oxidation state, and also metal ligand covalency. I will show you those more in a couple of slides. Then at highest energy and lowest intensity, we have what we call the valence to core. These are these super weak transitions, but they're super weak, which makes me sad, but they make me happy because they also directly report on the ligand electronic structure. And of course, chemistry is happening in the valence orbitals. So if we can directly probe what's happening, we can directly probe chemistry. And that's very cool. I'll show you some of the things that this can give us in a couple of slides. So we're going to ignore K-alpha and focus on K-beta and the valence to core. So for these K-beta lines, the first thing that they're sensitive to is the spin state of the absorbing atom. So as a fingerprint, what you can see here is high spin iron and low spin iron. These spectra look qualitatively very different. I'm not going to go into the physics of why these look different, but you can use it as a fingerprint for spin state. So if you have an atom and you don't know, is it S equals 1 or S equals 2, main lines can probably tell you that. They can also give us oxidation state. So this is a nice series of manganese oxides, D5 manganese O, or MnO, to D4, to D2, to D0. And what you can see is you have a nice smooth transition from the high spin spectrum in red to the low spin in black. So the main peak shifts to lower energy, and the satellite peak shifts down in intensity. So this gives us oxidation state sensitivity as well, in a way that is often more sensitive, or it can be more sensitive than the X-ray absorption edges. So that was an example here by the Robinson group here at Cornell, actually. They had these very complicated perovskite type structures. They had multiple different metals in them and different sites and different oxidation states, and they wanted to deconvolute what the different oxidation state and site symmetry compositions were of the different metals. They tried X-ray absorption, and they just didn't have the sensitivity to tell. So they instead did this K-data and XES, and by doing, what's the word for this? By looking at the different, looking at the amount of different components in this, they could deconvolute how much in each spin state and each symmetry state of the different metals they had in these samples, which was impossible for them to get out with even other X-ray methods. So this is a neat example of what you could do with mainline XES. Now, it would be great if I could leave it there, but unfortunately it's a little bit more complicated than that, because not only, or if you look at the series of iron compounds, these all have the same oxidation state, same spin state. But what you see is that these spectra all actually look fairly different. And so you see this iron fluoride looks very high spin. This iron sulfide does not look quite so high spin. And the reason for that is because these spectra are essentially sensitive to the spin density on the absorbing atom. So if you have ligands that bond to that absorbing atom that are very covalent, they can delocalize spin onto themselves and away from the metal. So the metal will look effectively lower spin than it really is. So we know that fluoride is a very ionic ligand, so it looks very high spin, that's what we would expect. But thiolates are very covalent, so they delocalized a lot of that metal character onto themselves, and that made the iron look lower spin than it really is. Now, you might think this just complicates things, but covalency is a really interesting property for chemistry, because it can tell us a lot about the bonding environment of an atom. And so we can use these mainlines to probe both absolute covalency and changes in covalency during a reaction. It turns out that this is actually quantitative, so you can quantify the splitting between these two peaks and relate that to the covalency, the d orbital population, in ways that are very difficult to get with other methods. Okay, so now we'll move on to the valence to core. So I said before, these valence to core transitions are coming from ligands that start out their lives in ligand-localized orbitals. So not on the metal itself, but on things around the metal. And so because we can probe those directly, we can learn a lot of interesting things about the chemistry of a complex. So most simply, if we think about what happens between nitrogen to oxygen to fluorine, these are just free atoms. As you increase the atomic number, the energy of both the 2s and the 2p electrons drop in energy for the same reason that we saw before. You have more protons in the nucleus. It holds on to those electrons tighter and tighter. If you look at the valence to core spectra, even all the way back in 1999, they knew that these valence to core spectra could give you very different signals depending on what the atom bonded to a metal was. So fluorine is different from oxygen, is different from nitrogen. And now, this might not sound like a very useful thing to tell, like this is just atomic composition, like that's not very complicated. But for very complicated systems, it can be very useful. So this is the enzyme nitrogenase. And if you don't know what nitrogenase does, is it converts atmospheric dinitrogen to ammonia. Makes it bioavailable. So this is a reaction that humanity spends about 2% of its annual global energy use to do industrially. So it's a very important reaction. And if we could take inspiration from nature to figure out how to do it maybe a little bit more efficiently, you don't need a lot of gains that have huge payoffs in terms of energy consumption. So we knew from crystallography that it had this very complicated cluster in the middle that did catalysis, that had irons and sulfurs and molybdenum. And we knew that there was an atom in the middle of this cluster, but we didn't know what the identity of that atom was. For various reasons, you couldn't see it with crystallography, you couldn't really see it with other methods. So for many, many years, there was a debate of what is X? Well, it turns out we could use the the identity sensitivity of valence to core spectra to tell what that is. So here we have the spectrum of this cofactor up top, and you can calculate what carbon, nitrogen, and oxygen would look like, and we see that you have a peak corresponding to exactly where you would expect carbon to be. So valence to core was able to answer this long-standing question of what is this mystery atom? So So if you have any mystery atoms, let me know. We might be able to figure out what they are. Can also do cool things like looking at, again, protonation state. Protonation can be difficult to find with other methods. So we again come back to this nice series of manganese dimers. If you protonate one of these oxygens, what you do to those orbitals is you split the 2s and the 2p. You drop one to lower energy, and you push some up to higher energy. Because these changes are on the order of a couple of electron volts, we expect that we might be able to see those changes in the valence to core. And it turns out that you actually can. You get one set of peaks up here for the ligand 2p, and one set for the ligand 2s. And in both of these, you see fairly pronounced changes corresponding to this electronic perturbation that we have from protonation. So similar to XIS, we can see subtle events like ligand protonation. I'm going to skip this because I don't have a ton of time, but you can look at bond activation as well. So it's dinitrogen. You can split dinitrogen into 2 nitrides, look at valence to core peaks, and see that happen in this process as well. Okay, so these are the kinds of things that you can learn from valence to core. I will pause again to ask for questions. Yeah. Nothing. You're all going to be experts by the end of this. Cool. Okay. So in the last couple of minutes, we're going to talk about the neat information that you can learn by combining these two methods. So, until now, I've kind of felt left out because everyone else has had really nice, pretty pictures in their talks. Lisa had her images, there's diffraction patterns, Jenny's going to show us all kinds of cool stuff, and I just have squiggly lines. Well, when we combine these, we actually do get some pretty pictures. So basically, when you do these methods experimentally, the setup looks exactly like you do for X-ray emission spectra because you use the same spectrometer to do that. So you scan the emitted energy, and you also scan the incident energy. So you vary both axes at the same time, and that's how you collect data. So data for this look kind of like this, so you get nice pretty colors. And what this is on the x-axis, we have changes in the incident energy. Whoops. And then on the y-axis, we have changes in the emitted energy. And there's a whole lot going on in this plane. And so I am a spectroscopist at heart. I like pretty pictures, but when I analyze data, I convert those into squiggly lines because I don't know what to do with pretty pictures for analysis. So if you take, you can basically think of this as taking a slice along at constant emitted energy. So you're changing the incident energy along this slice. You get something that looks like an X-ray absorption spectrum. If you do the same thing in the vertical direction along the emitted energy, you get something that looks like an X-ray emission spectrum. So when I analyze these spectra, this is what I do. I take cuts through these complicated planes and convert those down into spectra. Now, we give names for this. So for these vertical cuts, we call those resonant X-ray emission data. And for these horizontal cuts, we call those, again, physicists clearly named this, high energy resolution fluorescence detected, or HEXT XIS. So yeah, very fun. So now, why would we ever want to do this? Well, beyond a pretty picture, if we look at what HEXT can give us, here I'm comparing a standard XIS in black to a HEXT spectrum in red. And what you can see is that the HEXT spectrum is at significantly higher resolution than the standard spectrum. So down here in the pre-edge, in the black, it looks like you just have a single pre-edge peak, boring, not very interesting. But in the HEXT spectrum, you see that you actually have 2 different peaks. You have a main peak and a shoulder at higher energy that you would never see in conventional XIS. But in the HEXT, you reveal this. You also have much lower background. You can see you basically have no signal at all when you don't have peaks in the HEXT. And in the standard, you do have this kind of tail that swoops down to lower energy. So you get lower background and much better resolution. You also have overall lower signal. You can tell that because you don't really have noise in the standard spectrum, but you do have some noise in the HEXT. So at the expense of some signal, you get better resolution. This is particularly helpful for things like second and third row methods. So in XAS, as you go up in atomic number, your resolution goes down. For first row metals, that's not too big of a problem. By the time you get to things like molybdenum and platinum, your resolution has gotten really terrible. You can see that this is molybdenum. You don't really have a whole lot of interest going on in this absorption edge. In HEXT, though, you do suddenly see that you get pre-edge transitions and much better precision on the position of the edge. So before, it would be difficult to say even what is the oxidation state based on this molybdenum XIS. But with HEXT, you have much more precise definition of what that is, and you can compare even similar species in the HEXT. So you can, the HEXT allows information that you couldn't really get out from standard methods. You can also do really cool things like site selectivity. So this is a compound called Prussian blue. I'll let you imagine why it's named Prussian blue. But basically this has two distinct kinds of iron atoms in it. You have an iron that's surrounded by cyanides that's low spin, and you have an iron that's kind of outside that environment that's high spin. From those K-beta main lines, we know that those give different shapes. But in the same compound, they overlap a lot. So this is, you're looking at basically the overlap of the low spin and the high spin. They're not resolved, they're all kind of in here together, so it's not very helpful. But what you can do is if you sit your emission spectrometer to an energy around here, you can collect spectra that are selective for that low spin iron, and same over there that will be selective for the high spin iron. So you can actually collect XFs that are selective for each of those different iron sites just by changing the energy that you detect. No way you could ever disentangle this with conventional XAS, but with HEXT you can. So if you have a complicated system that has a metal in multiple different chemical states, you can use these two-dimensional X-ray methods to figure out what each one is doing. Okay, if we look at now resonant X-ray emission, it's a very similar story. So by taking those cuts through the plane, you can improve the resolution dramatically in the X-ray emission. This is particularly clear in valence to core, where before, looking at platinum in this case, you had just a single really sad, really broad peak that doesn't tell you anything about the system. But with the resonant, you sharpen this up into two very clear peaks and even a tiny little guy down there that now has a lot of chemical information that you can use to extract chemically useful information from this system. Running out of time, but this is basically an example showing you have that same kind of selectivity. These are two different platinum chlorides. Depending on where you detect in that plane, you can selectively probe one or the other. So this is HEXT and REX. There's only one very small section left, so I'll just go through this and then we can ask questions at the end. Take-home message here is that these spectra can be very complicated, but thankfully we have the ability to calculate each and every one of the kinds of spectra that I showed you. So whether it's XIS pre-edges, K-beta spectra, valence to core, or RIX and HEXT, you can use DFT or ab initio methods to calculate what those spectra look like and use the insights from chemical theory to help interpret your spectra. So they might look complicated, but we can have the computer help us out. Then, because you'll have all these slides, these are just some useful resources that might be useful if you're planning experiments or want more information. So I'll just leave that there, and we can end with questions. So thank you all for your attention.
I'm going to ask something of all of you. Let's all stand up. Because honestly, I don't know about you guys, but I stood up and I was like, oh, yes. Okay, stand up. I know. We all just ate. You might be a little tired, get yourself stretched, do a little wiggle or something.
You can sleep during Jenny's presentation and be awake during mine, okay?
Exactly. Cool. Okay. So if you do not study biology, go ahead and take a seat.
Oh, that's cool.
And that's what I thought. So that's absolutely wonderful. I am not offended. This should be a really fun talk. So yeah, I'm Jenny Wireman. I'm the macromolecular science director at CHEXT. We have a couple of beamlines, which I will talk about at the end of the talk. I was asked about crystallography, mostly because my background is in protein crystallography. If you're going to ask me what I would call myself, though, I would say a biophysicist. So I'm kind of straddle the interplay between X-ray science, which comes with the Synchrotron, and biological problems or biological challenges. So you'll see a lot of slides that will look really familiar. Thank goodness we share slides between all the speakers, and a lot of that is because there's some really great ideas that kind of flow between all of these fields, even if you're biologically squishy. So, let's see if I can use a clicker. Although,
You'll be better than I did.
Yeah. All right, so we're all familiar with this graph by now, right? We've seen this wonderful, what we can call a molecule, we'll call it a crystal or something, where it has different types of interactions. You know, we have our incident X-ray photons, we've got inelastic scattering, elastic scattering. So, and of course we have hard versus soft X-rays, but you guys have all seen this before, right? So we know, what did we study at chess? Which one of softer versus hard? I'm going to ask for audience input this entire talk, guys, so please don't be shy. So I'll call on people too. So soft and hard, yeah. Well, mostly hard, but we do soft and hard. Okay, so we're familiar with this slide. So I think Amlan showed something that was very similar to this, although I think I switched it on you guys because over here we have scattering. So I'm going to talk about crystallography, which is mostly diffractions. We'll get into that X-ray diffraction here. And then Amlan also covered scattering from in small angle scattering. So I will actually touch on this towards the end as well, because you will have the ability to go to a small angle X-ray scattering biological beamline tomorrow as a part of one of the demos. And since I do the squishy stuff, I thought I would at least give you guys a little bit of an insight into the scattering that we do on our biological small angle X-ray scattering beamline. So I will talk more about this towards the end, but what we're going to talk about, or we're going to listen to, is diffraction, which comes from crystals. So just kind of highlighting the two methods I will cover, which would be X-ray crystallography, mostly from proteins and macromolecules, but we will cover crystallography at large a little bit, so you guys will get a little bit of insight into that. And then we will talk about biostacks towards the end. I believe Amlan also showed this wonderful image of crystalline and amorphous and glass type materials. So, I mean, when you think of a crystal, you might think of something like what's potentially in, a ring that you might wear, or you might think of something like table salt. All of that, yes, is crystalline. But, metals also form crystals. They also form metallic glasses, which are not quite ordered, but there's some interesting features in there. Polymers also form kind of this kind of weird interface of quasi-order at sometimes, and then sometimes crazy stuff that happens on the edges. But I want to tell you guys a little bit about protein crystallography. So when you think of proteins, this is what your body is made of, right? So you don't have a whole bunch of crystals hanging out in your body. At least most people don't have a lot of crystals hanging out in your body, so we'll talk about what that looks like. For crystals in general, though, we can think about having a monocrystal, which is completely one single structure that's repetitive throughout the whole body. But then there's also polycrystals. And you can kind of think of, if you took something and smashed it apart, all the little pieces kind of have a little bit of difference. This would be a polycrystal. And you'll see that a lot of times in stuff that's formed in grains, so metals and other types of materials. So the grains are basically the bits that are ordered is one grain. And then a polycrystal would be a material with many, many grains. As a protein crystallographer, we look for monocrystals, so things that only have one repetitive pattern throughout the whole thing. And I'll explain to you why that's important in a little bit. But as I wanted to be a little bit broad, I want to explain also that there's polycrystals, so you can still get really useful information from polycrystals. I think Amlan also gave a little bit of an insight to powder diffraction. So you guys can go back to those slides and check out powder diffraction. So crystals can also be very small. So I talked about table salt, right? So table salt, you can actually pick out a single grain of table salt, probably like it, whatever. Cool. Protein crystals are really small. I'm talking about if you took one of your hairs and you cut it and you saw the radius of your hair, it's about that size, if not even smaller. And in fact, we study crystals that are on the order of nanometers in size at some beamlines. That's really, really, really small. I typically like to look at crystals that are about a micron and larger, but we do have some really fun equipment at other facilities study nanocrystals. Okay, so let's talk about how you describe a crystal. So there's a lot of words that come along in crystallography. So up here at the top, you have a motif. So motif is a repeating unit of pattern. So my friend Kelly, who thankfully provided me with a lot of these slides, has this gorgeous little cat, black cat. So I'm going to use this cat as kind of my repeating unit for my motif. So if I was to put this motif or cat on a grid,
it will kind of look like this. So here now we have these cats that are aligned on this repeating pattern in a grid. And so the grid itself would potentially, you could start at an imaginary point at every point in this pattern, and you could call that a lattice point. So it's repeating the same way in every single one of these, I guess, cat images. And if you were to draw a grid around it, then you could potentially draw this parallelogram around the cat. So this parallelogram could be this repeating tessellating unit. We'll do a little bit more of this in a bit. But of these cats, so and each one of these are exactly the same, and you can kind of tile them together. Excuse me. Into a pattern. So if you're thinking of a salt molecule or a sugar molecule, and you put that into a repeating pattern, it seems fairly easy. You just kind of pack them in real tight. But there's a problem when we go a little bit bigger. So if we go to something like a protein, this is a really, I think, I got this slide from my peer Erin Pinky. So if we take a light source and we shine it on something sticky or squishy or something like a germ, a cell, or whatnot, then the light that is reflected off of this can be then focused and then magnified in order to get basically a large picture. So this is microscopy, right? So you look at something and you're able to use lensing in order to blow up an image large enough for our human eyes to see. Okay? So that can work on things like cells. It can work on things like, mostly for cells. So this works for visible light, right? And electrons. So if you have light and you illuminate something like a cell, then you could potentially see the large scale, excuse me. See the macroscopic, I guess, aspects of said ugly little germ. What happens if we go smaller than that? So this is an ion channel. You should be familiar with it. It's in all of our bodies. This one specifically came from bacteria, but anything that needs to have potassium shuttled from one side of a membrane to another, and you have to do this, for instance, between the synapses of your nerves. That's how we transmit a lot of signals. It's how we help transit different kinds of molecules in your cells. So if you want to, for instance, channel something through here, this is a protein. This is a single protein. It sits in your cell membrane. If you were to take light and try to look at this and focus down the light and then blow it up into a macroscopic image, you will fail. But it's really difficult to see a single molecule or a single protein. What this looks like is more like this. So this won't happen. And it's because your diffracted X-rays cannot be easily focused and defocused at this level. Not impossible, but it's really difficult to look at a single particle. There are places that can, so the LCLS, the linear coherent light source, that does look at single particles, but it's a huge machine, and you want to be able to obtain all of the information that you can from this, and using a huge machine like this will oftentimes, look destroyed, but we need to find a better way to look at single molecules. So remember we were looking at kind of the different wavelengths of light and what we can look at. So, our eyes and we are very well adjusted to seeing fruit flies all the way to humans. You guys can all see me now. If we have some sort of magnification, we can start seeing, smaller and smaller organisms. I'm so sorry, guys. But as you get to smaller and smaller wavelength, you're able to see smaller and smaller particles or proteins. And this just happens to be in the same regime as X-rays. So X-rays are specifically tuned to be looking at kind of atomic level resolution structures. With protein crystallography, it's an established method that can give you atomic resolution structures. So this means that if you were to have two atoms, you'd be able to distinguish them if you have an angstrom resolution. Two different electron densities that would demark where different atoms are in a protein molecule. So this is just an arm of a protein molecule here. And as you decrease in resolution, you'll see that resolution actually begins to overlap, and you're not able to distinguish the two different atoms from each other. So with protein crystallography, you're able to actually see the individual atomic resolution, and it's truly unmatched by any other technique, including cryo-EM, getting down to a sub-angstrom resolution. So it's an established structure, this established method. Protein crystallography has been around for almost 100 years now. So crystallography has been around for 100 years. Protein crystallography has been around for about 60 years, I think. So, but what is it about crystallography that makes it so unique to light microscopy, right? So if you can't see it with light, you can see it with, if you can't see it with visible light, but you can see it with X-rays. Why are X-rays and why are crystals so necessary for crystallography? The difference is, if you take a crystal, so each one of these little gray blobs can be considered one protein. So if you take and you stack all of these together, you're essentially amplifying your signal from within this crystal. So crystals are just highly regular 3D arrangements of atoms or molecules. And if you were to take 1 grain of table salt, that's about 3 quintillion molecules of sucrose. So you're amplifying your signal by about a quintillion. But in addition to that, you're creating a really ordered substrate that you're illuminating with your X-rays. When you have an ordered substrate like that, you actually create a diffraction grating. Think of it as a diffraction grating. So if you have an X-ray source and you illuminate a crystal, it'll actually give you a pattern off of it. So you won't get to see the shape if you look at the image. It's not the shape of the protein that you're actually looking at. What you're looking at is a transform from the real space of the crystal into reciprocal space, right? So this diffraction pattern actually contains information about the atomic scattering components of the crystal. Can someone tell me what the atomic scattering components of a crystal might be? What do X-rays scatter on? Do they scatter off of electrons? Maybe? We talked a lot about electrons that scatter. So all right, I'll give you guys that one. All right, so they scatter off the electrons. So when the X-rays hit the crystal, they're actually interacting with the entire electric structure, so the electronic structure, the density of electrons that are in a crystal. And so it's 3 quintillion different repeated patterns of electron densities within a crystal. Okay. So when you look at a protein crystal, this will look very different than if you're looking at something that's a small molecule crystal. And the reason being is when you look at a protein crystal's diffraction, you actually see this beautiful pattern, and you'll see there's kind of these lunes. So, and you'll also see beam stuff. I'll talk about these components in a little bit. But it's a very different image than if you were to see, for instance, a powder diffraction image or a small molecule image. We have a lot of spots here. So, and that is because of how much electron density there is built within every repeating unit of your protein throughout the entire structure of the entire lattice of the crystal. So in order to solve your protein, so if a protein looks like this, it's actually a model of a protein, not an actual protein, but semantics. You go from having some sort of a diffraction pattern, and you have to somehow get this diffraction pattern transformed into an electron density, right? So the goal is to eventually come up with this 3-dimensional structural model for your protein. And what most structural biologists will do is fit an atomic model of something very similar to this into this electron density. Because remember, when you go from this spots on an image and you do a Fourier transform, you're only looking at the electronic density here. It says nothing about what the actual components are in there. You just get these blobs of where the electrons in this crystal are. So you go from this image to something that looks like this, and then you fit a model or kind of a chain of amino acids into this, and you can actually see, oh, there's a ring. So you can see there's a hole in the middle of it. Okay, so this is kind of the very, very simplified version of what crystallography is. You grow a crystal, you take a fraction pattern, do a Fourier transform back to the electron density space, and then you fit a model to it to get your eventual model out of the end. But it may be no surprise to you, the first thing you need to do is grow crystals. So these are all protein crystals. So this is made from lysozyme. Lysozyme is the main component in egg whites. Delicious. I've never tried to eat a protein crystal. I might, but I'm not going to today. This is lysozyme. Down here is thaumatin. Thaumatin is about 4,000 times sweeter than sugar is. To imagine, like high fructose corn syrup is about 1/3 as sweet as thaumatin, so these little buggers are really, really sweet. I believe this is catalase. Not remember right off the top of my head, but all of these are protein crystals. To be completely honest, one of the most difficult parts of protein crystallography is just getting to this point. I've known a few friends who have spent 6 years trying to just get the crystal. It's really difficult. And that's because every protein is different. A lot of them do like crazy moving things, and so you have to find the right conditions to pack it into that repeating unit pattern, right? So what that looks like is if you're to look at the time course of crystallization and the amount of energy, at some point in time, you need to put them into some sort of an ordered phase. So it's actually energetically favorable to grow a protein crystal, or to grow a crystal. So this is true of all crystals, not just proteins. It's true for any kind of a crystal. So from kind of a random assortment, you can start to get clusters, you can get non-specific aggregates. At some point in time, you will get large and specific aggregates, and then as you kind of go over this energy barrier, energy hump, you will go into an ordered phase, which then crashes out into crystals. Okay? So this can be extended to metallic systems, salts, anyway. So this can be applied to any kind of crystallization. Okay. So at the base of it, though, is what we call the unit cell, and it's that repeating box. Remember I showed you the cat, so this would be the unit cell, the cat in that lattice crystal. But there's a lot of nomenclature behind the unit cell, and it's usually defined by 6 variables. They have A, B, and C, which define kind of the vectors that give it the vectors of distance or size, and then the angles alpha, beta, gamma. So this determines kind of what the shape of your unit cell looks like. So then you take this shape and you tile it together. In other words, you literally copy paste. You take your Lego blocks, you build up your repeating unit, right? From this single tessellated unit or unit cell. From there, we keep going. So the only packing arrangements of any object can fill space, generate single crystals, and you can look at 3 or 7 different crystal systems: triclinic, monoclinic, orthorhombic, trigonal, hexagonal, and cubic. And then those lead to 14 different Bravais lattices. From there, you can have 230 different space groups. The cool thing about proteins is they're made out of a string of amino acids, and those amino acids all have a hand in this. This means that the way that the amino acids are built, they're all with a very specific chirality. This means they're all built with left hands. They don't have left hands and right hands, or a mix of the two. It's all left-handed. So that actually eliminates for protein crystallography down to 65 and enantiomorphic space groups. And they differ in the amount of different ways that you can arrange them. So, a cube can only be arranged in so many ways. But if you have something that's triagonal or hexagonal, you can kind of pack them a little bit differently than you can with rhombic. So the degree of the space group and the complexity of it can dictate how you pack all of these unit cells together. So let's actually look at what this looks like. So depending on the symmetry of the crystal, which is what we just talked about, the unit cell might have many copies of the building block that we want to study. So the building block is these blobs or proteins. So in that building block, you can have, in the unit cell, you can actually have more than one cap, basically. But what we call the fundamental building block is the asymmetric unit. It's the smallest possible unit that lacks any symmetry operations. Symmetry operations are like mirror, right? So your hands are a symmetry operation, it should mirror your hands. Or rotation, or oh my gosh, totally. Anyway, so okay, we're gonna do a quick pop quiz. So what's the asymmetric unit and what's the unit cell? So this is an Escher image. So does anybody want to try to point out the asymmetric unit in this image? Ernie's giving me a clue over there, but do you guys know what the asymmetric unit is? Is it one of these birds? Is it two of these birds? Does anybody have a guess? Two. Close, but you can take the white one and just kind of flip it down, right? So it does a rotation and it does a mirror, right? So it's very close though because they're different colors, and maybe that's what kind of made it a little bit difficult. So the asymmetric unit here is one bird. Okay? So this is there's no other symmetry operations that can reduce that bird, that can be reduced from that bird. So that bird can be repeated, it can be flipped to be this blue one, it can be translated up to be that one, right? So this is the asymmetric unit. So if I was to draw what the unit cell looked like for this, now I'm just going to take a random spot. So if I was to go from one repeating part of this image to another, I'm going to take basically from that peak to that peak, just because it's a really easy kind of point to look at. I can say that peak, down to that peak, down to that peak, down to that peak. Or maybe it's the edge of the wing. So let's call that the unit cell. So in the unit cell, if you were to look, how many of the asymmetric units, that's that bird, how many birds are in that asymmetric unit? Any guesses? Two. Perfect. That is awesome. There are two birds in that asymmetric unit. And then if we wanted to, we could actually tile this asymmetric unit through the whole thing, right? So now we have a lattice where we have these lattice points that we've designed on our own, and that's totally fine. We'll do that again. But the asymmetric unit contains, this unit cell contains two asymmetric units. So if I was to cut it out, now we have, basically this is one unit cell, it has two asymmetric units in it. And what I can start doing is copy pasting it. So there we go. I just took it and I copy pasted it next to it. So I didn't take this image, all I did was copy paste it. You can see I'm not lining stuff up that well. But notice how when I cut it, I didn't cut it perfectly. But that happened, I can keep copy pasting it, go up, and go to the side. Notice this weird line that's there, I don't know. But anyway, so I'm just taking this and copy pasting it, and notice that it lines up. So we can keep doing this, and I could fill out the whole page, but I got bored after a while. You can only copy paste so much before you're tired. So, okay, fine. But I kind of arbitrarily picked the beak, right? So the beak wasn't necessarily, I didn't have to start the asymmetric, or the unit cell. I can actually move where that point is. So this is also a valid unit cell. Because I've defined, and I just took this and I moved it, I literally defined the angle from here to here to here. So I define the angle of these lines to each other. I determine the length, because I drew those out from the repeating unit of the peak in each one of these. And now I can take that unit cell and move it anywhere in this image because it is the unit cell of this pattern, right? So that unit cell is valid no matter where it is. Let's do just one more, although I may be, ooh, I'm running close. Okay. Who wants to guess what the asymmetric unit this is? Fish? You think it's a fish? Three fish. So you think it's these three fish here maybe?
Yeah.
The asymmetric unit. So the asymmetric unit cannot be reduced any further. But I could take this fish and I could just rotate him and he looks up here, right? I mean, so yes, the colors are kind of tough. Ignore the colors, right? So you have this one, you probably flip over there, but you can also cut the fish in half and you can flip this side over onto that side, right? So the asymmetric unit for this is actually half a fish. Because that half a fish can be rotated, translated, mirrored, you know. It can be every single one of these other pieces. So what do you think the unit cell looks like? So now the unit cell, is something that you can tile it together, right? So here you've got your one asymmetric unit. What do you think the unit cell looks like? So that. So if I take this, can I tile it here?
Can you rotate it?
I don't know about that. If I was just to take this and copy paste, I don't think I can make it look like this one or like this one. It's a mirror. Well, it's a mirror, right? But with the unit cell, I have to copy paste. I can't take a unit cell and I can't mirror it, right? So that's actually not the unit cell. The unit cell is this. So check this out. So if you take this and you copy paste it, suddenly I can fill out this whole picture. Cool, right? Crystallography guys, right? It's the coolest one. Go ahead and say it. Coolest technique. I'm just kidding, I'm kidding. They're all really cool. But, okay, so here, now you guys can see. So unit cell, copy paste. Asymmetric unit, you can take that bugger and flip it around, translate it, you can mirror it, you know, have fun with it. Okay. So let's go back to x-rays. My husband loves Pink Floyd, so, you know, I try to stick with Pink Floyd, but look, it's diffraction. Okay, so you're taking incoming light, you're breaking it up into components, that's a form of diffraction, right? So, but, I mean, it's a prism, right? So a prism is actually a crystal. Okay, so incoming radiation is split into discrete wave packets by the object. The structure of the object becomes encoded in the distribution of the diffraction, right? Okay, so in other words, there is a Fourier transform of the object through this crystal, okay? So through its reversion, so you're taking light and you're somehow transforming it into, well, here, a rainbow. But through this crystal, you're doing a transformation on it. So the kind of reverse of this is what a lens does, right? So a lens takes light and it focuses it down to a point. So it's actually transforming this from parallel incoming light to something that is not parallel, okay? So in the diffraction of X-rays, what you're doing is you're creating a transformation through the diffraction pattern. And remember, when you do this diffraction pattern, you get this image. Oh, it's been shifted. How unfortunate. Okay, let's just pretend like this little white circle actually coincides with the red circle. Okay, so for a protein diffraction, and now again, bias on biological, but this is true for any diffraction image, you get reflections. So these reflections are all of these dots. And these dots are recorded X-rays, okay? So you've got recorded X-rays and you notice that they're in a pattern. Really cool, right? So that pattern comes from that repeated pattern within your crystal that you have. And just a note on resolution, and I'm sure that others have talked about this. So the center of the image is where the X-ray beam goes through. In diffraction, the further away you move, the smaller distances you're probing in your material. So in the crystal, The further you go out, the higher resolution image or part of the crystal you're seeing. Okay, so and then you notice these lumes, and I pointed those out earlier. These are things you'll only see with crystals with large unit cells. So when I say large unit cells, in comparison to, for instance, salt or sugar, they have a very small unit cell because a repeating unit of salt, sodium chloride, is a lot smaller than, say, something like lysozyme, which is a very big molecule compared to salt. So you will see these beautiful lumes and whatnot due to the fact that we have these very large unit cells. You'll also notice there's beam stop shadow. I think either Amlan or maybe Chris even talked about needing to shadow. You don't want to hit the detector. This is a multi-million-dollar instrument now most times, so you don't want to damage your detector by having a very strong X-ray beam impinge upon it. So let's take a look at what these reflections look like. What a reflection actually looks like. So this is two-dimensional, right? So if you were to just take a one-dimensional scan, a line scan across this, it would be a one-dimensional image like this, right? So at the very peak of this would be the very center of that spot. It's the very brightest part of it. And we can actually measure these kinds of distributions given that we have small enough pixels to resolve. Like each one of these squares might be a pixel. Okay, so each of these reflections gives us two types of information. First thing is that it gives us a position from the center of the beam. So from the center of the beam, we're able to measure out from it, and this gives you a Miller index, which is HKL. Get into that in a second. It also tells you an intensity, and this gives us information about the unit cell contents. So remember, the unit cell would have more than one asymmetric unit, right? More than one herd. But this intensity will give us information about the unit cell itself. All right, so we're going to rewind a little bit. You guys remember Amlan, and I think Chris might have also talked about Bragg's law. So here we have Bragg's law, and we're going to simplify our really complicated protein crystal down into these planes. So these planes, which would be, for instance, from one side of the unit cell to the other, or it could be from one part of your protein to the exact same part of the protein in another unit cell. So those are repeating patterns, and they're separated by this distance d. Now you've got light that comes in at some specific angle, and due to physics, it also leaves at the same angle, right? We've got a mirror, basically. Okay. So we did talk about Bragg's law. I think you guys remember this beautiful equation. I thought about it getting tattooed, and then I thought, wow, what a jerk. Okay. So what you have is incoming and diffracted wave. You've got this angle theta. Now, again, physics, so I won't do too much geometry. Now here we have basically the same angle here. We can make a little right triangle out of this. You know the distance AB and BC. You know that AB plus BC equals some integer n. Okay, go with me on this. And the wavelength, right? So this is how many times this wavelength is within this kind of path length of from A to C, right? Okay, and it's just some integer. So since we know via geometry that AB is equal to some D, that's that distance between our planes, which makes up the hypotenuse of our triangle, our right angle triangle. Okay, since we know that AB equals D sine theta, and since we know that these two things are equal, then we know that n lambda equals 2D sine theta. So this is where Bragg's law comes from. It's really super easy, right? You guys are like, yes, I've totally memorized this, and I'll talk about it to my friends. I know. So fun. Okay, so this is how we're able to relate refracted X-ray beams to crystal components, right? So we have incoming X-rays, outgoing diffracted X-rays, which we record with our detectors. Because we know that the energy, or the wavelength, that the incoming X-rays are, and we detect them at some distance away from where the crystal is, we can then calculate what the distances between these you're way ahead of me. So anyway, so these lattice planes are then defined by the Miller indices HKL. So this is what I was talking about on that other page about the HKL indices within the image. You know, the center of the image and the distance out. Now, remember how I said that the further you go out, the smaller distances you're probing in real space, right? So here we are at D minimum. That's where the B stop is. The further you go out, here's 10 angstroms, 5 angstroms, 3 angstroms, 2 angstroms, and it can keep going to under an angstrom. Okay. So according to Bragg's law, that's what we just talked about, the spacing between your lattice planes within your crystal is equal to this equation. So the reflections are corresponding to high resolutions, that's out here, that's below D minimum, so below D minimum, have larger Miller indices and are far away from the center of the image. Everybody on board? Okay, cool. All right, so I apologize. This is one of my favorite equations. This is a Fourier transform. Okay, but I apologize. It is a fun and beautiful equation. All right, so when the X-rays are diffracted, they're diffracted by the electron density. So now what you can kind of see fit in here is a green kind of wire pattern. That's a model of a protein. But here you have the actual electron density. So when the X-rays are diffracted by the electron density function is obtained as a discrete Fourier transform of the structure factors. Okay. Each reflection in that image I showed you, those spots, are defined by a structure factor, and it's related to the measured intensity I. So, okay. Each spot in that image has an intensity. You measure that with your detector saying, I got so many photons in that spot. That is actually the square function of the structure factor. Of course, there's something missing here. So, you have this beautiful Fourier equation. You go from real space, and you detect all of these points. So, at each point in real space, the density of these mesh things, is calculated from all the structure factors. The structure factors, when you put them into 2D, when you record them with your detectors, loses the phase. Now you're recording it in 2D on a detector, and the phase is lost in this measurement. So this is called the phase problem. So remember earlier when I was like, oh my gosh, we have to take a model and fit it to this electron density. Part of that is we're trying to recover the phase information. So there's two big methods to solving the phase equation here, right? So the first one is you just use a known structure. You take something that's really similar to it. So like instead of your protein going like this, maybe your protein goes like this, okay? Or, sorry, if your protein goes like this, and there's a known stall structure and it goes like this, then take that and try to fit it to your electron density and see what happens. You can recover the phase if it's close enough. All right, so it's kind of borrowed from a similarly known structure. This is the most common structure or way that people have been solving for the last 30 years, let's say. In the last 2 years, they've been using AlphaFold. Ooh, all right, that's a cool thing. AlphaFold. So AlphaFold, how many people know about AlphaFold? Oh, okay. All right, so AlphaFold is this wonderful algorithm that takes a string of amino acids and says, this is what your structure is supposed to look like, based on the last 60 years of structures that have been deposited in the protein database, which is this very large database of proteins. So we've taken the structure of how proteins have been folded and what the shape of those are the last 60 years and predict how any string of amino acids will ever unfold. So now people are using that to do molecular replacement. Now, if you're a masochist, you might do de novo structure solution. And you can do this via a substructure analysis. That takes a very long time, years sometimes. Or you can use direct methods, and this has been done at CHESS. And that's just by using a difference between reflections based on wavelength. So remember how Bragg's law talks about the wavelength. So at some wavelengths, there's actually differences in in the phases, or sorry, in the information encoded based on, for instance, heavy atoms that are within your structure. Okay. Have I completely lost everybody? Yep, all right. No, that's good. All right, so that's how you end up solving the phase problem, and from there you can get structures. Yes? Oh, 5 minutes? Wait, okay, we'll be quick. So, if you're really interested, tomorrow when you go to a demo, there's a beamline that is right next to the BioStacks demo that you're doing, where we do crystallography for proteins. So we do Vermont Standard, we do serial. You guys can check out the slide on your own, because I think we're providing them. Okay, good. Check it out on your own. So, let's go back to this first one that I talked about, how we do X-ray crystallography. We just talked about all that. Go to 7B2, it's right next to the beamline that we'll be doing a demo on BioStacks. Okay, now for something completely different. Let's totally forget about unit cells. Let's totally forget about the asymmetric unit. Okay, so if instead you just have these random proteins floating in solution, they still have some sort of shape. There's still distances in there that you can look at with proteins. And instead what that does is it actually creates this like shmeary sunset. You'd be really cool if you took it in half of the beach in front of you, you'd be really happy. But there's this beautiful pattern, and what this gives you is a scattering profile. So the scattering profile is based on the different distances you can measure of an envelope, right? So this also works for things that are not proteins. So I just wanted to kind of stick in a quick slide where you have different, if you're going to take a radial, so radial 1D, oh my gosh, graph of what this looks like, then you would have this beautiful graph here, where you've got Q space, which is the distance from the center of the beam outwards. And it can give you, depending on the different regions, information about the size of your protein or molecule or grains. You can look at the size of them, you can look at the shape of them at some level. And you can look at interfaces. So this is a much more general description of this small angle X-ray scattering. Small angle X-ray scattering means that you have X-rays coming in. You guys saw this already, so this is just a reminder that if you place a detector very close, you can get wide angles. If you place a detector very far away, you can get the smaller angles. And this, of course, gives you different information. Wax gives you more of the interatomic structure versus SACS. It gives you more kind of the larger shapes and size and whatnot. And you can know if things are clustering together. It's really cool. So tomorrow at 7A1, you'll be able to do a demo with Richard Gilliland. You'll see his face on the last slide for BioStacks. So again, this gives you an idea of the envelope. It can give you radius of gyration, it can give you molecular weight, it can give you a low resolution particle shape, and a degree of folding. So say this thing actually folds onto itself. No, you can see that. And again, here are these wonderful plots that show you kind of the, I don't have a diffraction pattern, or a SACS pattern on here. Should have done that. We can get kind of these different ideas. These correspond to these. So the shapes of things can actually be inferred from these graph shapes. Oh, never mind. I think I'm missing a slide. I very much apologize. So what you'll be doing tomorrow is looking at these kinds of patterns and getting scattering profiles from some kind of protein molecule that is floating in solution. You will do this with Richard Gilliland. He will be at 7A1. If you're curious about protein crystallography, he's Steve. He will be at the next beamline. Not doing protein crystallography, but that's the beamline we normally do. If you have any other questions, you can ask me about any of it. I will be around today and probably most of tomorrow. And I hope I gave you a little look into protein crystallography, some crystallography at large, and a little bit about small molecular.
My name is Ernie Fonts. I'm one of the scientists at CHEST. I've been here 32 years. Can't get away.
Did you say
32. Yeah, I know. Sorry about that. Sorry. Some of you haven't been alive long enough to know when I started at CHEST, but it was around. It's a lot better now. I'm going to talk a bit about writing proposals, but you can laugh at me. That's okay. I like that. That's okay. Wait, she's going to spit it out. She's going to spit it out. Anyway, Chris asked me to do this. We've done this sort of tag team a few times. How to write a proposal. So I'm gonna take some of Jenny's scripts. So how many of you have written proposals? Any type of proposal, like even for your PhD thesis, you've written proposals. Okay. How many of you have written proposals to get funding from government agencies? How many of you have written proposals to get beam time at a very expensive X-ray source? Okay, well I'm going to talk. You've done a lot. Jenny's shut back there. Okay, so yeah, I'm going to talk about writing proposals. I spent a lot of my career has been writing proposals, but that's because I moved into management at CHEST. But as scientists, you will write proposals, often to get funding or to do some new experiment or new project. So I'm going to talk about writing a proposal from different points of view. This started out. This is the first time this was given. You'll see some of my history in these slides that are quite dated, but I've updated the ones that had to be updated. It started as a discussion, so please, like, if something is not clear, open your mouth after you swallow your food and ask me a question, okay? Oh man, I'm cruising. So before you start writing anything, a proposal for X-ray beam time, you have to have an idea of what you want to do a project, and whether or not CHEST can help you get that information, right? So that we're going to start with how the CHEST website helps you move along this route here. Now I'm going to jump to the bottom. Once you know what you want to do and that CHEST can help you, you're going to write a proposal. And I'm going to work you through some of the mechanics of writing the proposal. But in the middle there, you see call the beam line scientist. So there are a few times when all I'm going to say is call the scientist. Or call Caitlin Towner, who's the CHEST user administrator. You're going to meet her, overlap with her a lot tomorrow. She couldn't be here today. And at the end, the last slide, I have some quotes from her. Really good takeaways. But in the middle, call the beam line scientist. Some of what I talk about is just general good writing, so there's no secret to generally good writing. But for beam time proposals, there are some things like really particular types of information that the beam line scientists need in order to get you into the system. So we'll get to that. But let's start talking about just defining your project. So I'm going to use this obvious mechanism on some of my slides where in the upper left, you've got what you'd find on the CHEST homepage. I didn't write the URL, www.chest.1 and there's just a pull down for users in this really nice menu. We'll go through some of these things, not all of them. But if you're a prospective user, you start here. And so this is the page that would come out if you go there, navigate there. And so this starts to tell you about getting beam time in CHEST. It's called beam time. I'm going to use that word over and over again. Time when you're using the X-ray beam time. And so first thing I'm going to do is just jump into this first. Notice there's some really good things here. This is really the outline of my talk, almost. Planning your experiment, proposals, how to submit, how it gets reviewed, etc. I'm going to jump into this first one here, just talk about thinking about your experiment. So on this first slide, or this first page for planning your experiment, there's some really good questions. So if you haven't planned an X-ray experiment, I suggest the following. You take your phone and you put it on record and you say, what is the research problem? And then you just say what you're going to do. And then the second, what stations are appropriate? That's getting a little specific, but keep going. How mature, what samples are you going to bring? What experimental conditions might you need? Temperatures and pressures? You're scientists, right? These are the important parameters we need to know. What's going to be measured? This is sort of a leading question. Probability of success, 100%. And will the results be presented, and what's your timeline? So these questions just start to shape what are you going to do, get you to think about it. So this is sort of a prompt. Now once the other prompt is look at the beamline directory. And so the talks you've heard today, there are clearly different types of X-ray techniques or measurements that are supported at different beamlines. And so this page, which is changed and updated as it needs to be, tells you that at certain beamlines, there are time result studies for manufacturing processes of structural metals. Okay, and so the ones Jenny talked about are, where are you up here? There's the biostats. Here's the HP bio micromolecular crystallography. So if those are the experiments you want to do, you want to pick these beamlines. Now, beamline acronyms, there are many of them. I'm going to just jump into one called FAST, which stands for forming and shaping. So again, I'm going to click on this FAST and jump over here. So now when you click on FAST, there's usually a really nice explanation of what the beamline can do. So nice pictures. There's a pic. Usually this link here leads to a page written by the beamline scientists explaining what they're doing, how they created the beamline, what its capabilities are, what they're hoping they can help you with when you come to CHEST. And you see there's a lot of detail. I mean, laser powder additives, what types of tensile systems, what types of acoustic mesh. I mean, lots of details, lots of details. That's why I say talk to the scientists, right? Because if you haven't ever visited before, it's hard to even know which X-ray detectors you need for your experiment. So if you hover over this Kate Shanks, or the beamline scientist name, you'll actually see their email address. We'll click it, go open it, and send them an email and say, I need to talk to you. I want to do something, and maybe it's your beamline. So that's just how you get to the beamlines. Louisa Smieszka, one of our other scientists, said, sometimes people don't have all that information. They just call up, and I say to them, show me some data that you want, that you think looks good, like you want to do this too. So Louisa has worked with people where they just sent her a link to a paper, and they said, gee, I'd really like to go from 20 to 70 degrees in 2 beta. And she might say, I can or can't do that. So you've already created a conversation, and you can start to think about where your experiment, which beamline of your experiment is served on. So sometimes it's only a picture. But kindergarten, here's a picture. I want to do this. Where should I do it? And that's enough to get started. Anyway, now you have an idea what your project is, or you walk with a scientist to know which beamline it can go on. Now it's time for you to write something, because we need a lot of information from you, and I'll explain what that is. So you can't write unless you know who's going to read it, and maybe why, and what are they looking for. So these are sort of, in my mind, these are the 3 prompts. Even when I prepare to give a lecture, I'm like, who's going to be here? What do they want to learn from me? What am I going to do? So I'm going to, pretty trivial outline of my talk. I'm just going to talk about who's interested in reading your proposal and why. I think those are really linked. So that's my number 1 topic. What are they looking for? That's important, right? Because what are you going to write about? And then maybe at the end, we'll have enough time to talk about who's keeping time. That clock, by the way, is not.
Don't use that clock.
Okay, thank you very much. I'll keep doing this. How about that? You all wonder if I'm checking on my wife. Okay, so let's talk about who and why. So there are 4 audiences for your proposal, your X-ray beam time proposals. And just to fill you in on them, there's the user office. And we'll talk about what they're looking for. There's something called the safety subcommittee. And they're really, they oversee a lot of all the work that goes on at CHEST. And they have to make sure that whatever you do and whatever we do, or whatever's happening next to you when you visit CHEST is being done safely. There's something called external peer review. We'll talk about that. Those are other scientists that are going to look at your proposal and say, oh, this is great, do this. Or it's not good enough, please explain more. And then finally, there are the beamline scientists, and I'm going to explain this acronym. I think it stands for Beam Time Allocation Committee. Thank you. So they're the ones that might decide, you come this week, you come the next week, you come the week after that. So that's a beam time allocation, it's called. In gray is the process, right? So I don't want you to read it, but I worked with Caitlin on this presentation, you have to understand that what you write is going to be looked at by a few different audiences. So let's just, in a simple way, walk down, and I'm going to use that little arrow at the top to sort of tell you this is the audience. So the CHEST user office, they're really interested in your proposal when it comes in. Is it complete? Do we have all the information we need to understand what you want to do and make sure that you can come here and do it? So the user office is going to be really interested in completeness. There's a parallel path. It goes out for safety reviews. So there are people inside the lab who are assigned to be part of the safety committee. Jenny's one of them. Thank you for the hand. Yeah. And they will check to see, is this safe to do this in our lab? Do we have the safety protocols or the conditions that are needed so that you and everyone else in the lab can be safe? There's another parallel on the left side. There's something called peer review. Our funding agencies require that CHEST allocates the X-ray beam time to proposals that are deserving. So that's why you're doing this proposal. You're giving us information so that we can send it out to people who will say, this is good work, let's do this. And then finally, it comes back, and the Beamline Allocation Committee and the Beamline scientists, they take the information from safety review and peer review, and they say, okay, now it's a project. Now we're going to come and do it here in the lab. And so they need to be notified. They need to know a lot about what you're going to do, which we'll start talking about right now. So what you're going to do is going to be written into a proposal. And it's a form on our website. It has a lot of structure. You're going to get there by starting your user. So you're going to start with user portal. I'm not going to walk you through the mechanism of doing all of these steps because I think that's pretty straightforward. You're all scientists, you'll all figure that out. I'm going to talk about what you're writing rather than how to write it. But you have to log in or register if you're a first-time user. Again, the user office can help you with all of this, and there's a lot of online help. Once you log in, so you see here, I'm logged in, current response, I'm logged in. I'm not really a good prototype of user. You can see that I've written 3, so if you go in, this is userdb.chess, you'll see the URL on some following pages. But if you go in under proposals, and then you get a prompt called My Proposals. And I'm going to describe some of these pages a little bit in detail. When you have proposals in our system, they are there. You can work on them, you can edit them. I think you can delete them. Gosh, no, says Chris, no deleting. Okay, they're there forever. So you see how many times I've given this talk. In 2015, I created a perfect example proposal. And then in 2019, I created another one. And then just a couple of days ago, I created a third example proposal for this talk. And so these are all being worked on. I've never finished my proposals. So I just start them and I tell you about them and then I walk away and hope Chris does this next year. Oh, I got that in. Yeah. But anyway, so I'm gonna just show you. So there are some that I'm working on. That's these. There are some that have already been submitted and they're under review. And then of course you click the button called New to start a new proposal. When you do, this is the prompt you get, and I actually like the structure. This was developed after I left being UserDB manager. This is a really nice, so this is the page where you're building your proposal. It has really nice prompts. It has 10 sections you're going to fill out. So these, I'm going to walk through some of these sections and describe what's on the proposal, because that's why you're at this talk, to learn how to write a proposal. What's really nice about this prompt is that each of these, in yellow, every time you click on one of these, you're going to get something new over here. And in yellow is the stuff that's required. And so it walks you through very nicely to make sure you fill in the minimum information, minimum amount or maximum if you want. At the bottom of each of these pages down here, there's a button that says continue. This doesn't light up until you've finished the page. And so once I get through the essentials, which are just the title, a proposal type, and I identify myself as Ernest Sponsor of Cornell University, then I get a check mark. And so as I work my way through, this will go from 10% to 100, and then I can click a button and submit it. Pretty straightforward. I'll just mention now that I haven't ever, if you move from one university to another, you have several affiliations. So you might be a grad student the first time you submit a proposal. You might be a faculty member somewhere the second time you submit a proposal. You might be President of the United States the third time you submit a proposal. I mean, these things happen. So we had to give you a way to have multiple affiliations. As you move to different universities or different careers, you can have a different affiliation. As you can see, I've had only one miserable affiliation in my life, where you just take it away. You can add other people too. I can be someone else. I haven't thought that. So now let's talk about what are they looking for, right? What is on those 10 pages, sub-pages? And so this is the what part. To do that, I'm going to bring you back to the top of UserDB. Oh, now you can see the URL, UserDB, one word, all small letters. I'm going to bring you back to the top page and click on, everyone hates these things, but I like the frequently asked questions on our website. It's got at least one, but you see that it's not highly filled out, but I'm going to zoom in on one. So under the frequent, I want to find out what they want from me, right? So if you're curious about that, click on that, click on this one down here. How is my proposal reviewed? There are 4 criteria that are used to review your proposal. And you should all know them because that's what you're writing towards. We need to understand the scientific and technical merit. What are you going to do? Why is it worth doing? Do you actually need chess? If you need an electron microscope, you should not come to chess. But if you need X-rays, you come to chess. We need to see your experimental plan, and we need to understand the expertise of the group. That tells the scientists how much help or hands or other help that's needed. And you'll see now, I'm going to use these 2 boxes, the audience and the review criteria, and sort of walk you through, as you fill in the proposal, you're answering, you need to know the audience and know what they're looking for. So let me just use this simple crutch to move along. So now this is a proposal. I'm not using mine, because mine was trivial and silly. I'm using a couple of really good examples that were in the database. And so let me just walk you down the page and then we'll talk about who's interested and why. The essentials are, of course, the title and the principal investigator you have. It asks you to predict or forecast a schedule. How many number of 8-hour shifts are required? This is where it's really good. Really, it's essential to talk to the beeline scientists. Get an idea of what, how much time it will take. 15 shifts or 15 years, there's a big difference there. And then it asks you to identify the investigators, and we are asked still, funding sources. Right? If your work has funding from other agencies, we need to know about that. We have to report these things. That's why we know this. Who's interested in all this information? The user office is interested in, because we need to follow up, we need to find you, we need to know the title, we need to track it, we need to report the funding information. But also this starts to tell reviewers that you have an experimental plan, you've thought about how much time you need. It starts to tell you about the expertise of the group based on the collaborators. Moving down the list, stations and techniques, you have to pick one of those experimental stations appropriate to the science you're going to do. This one is 3A for fast. Now here we're getting into some real meat, right? So now you have to start specifying the specimens that are going to be used and the materials you're bringing. And these are of the real, I'm going to focus in on these on the next few pages. The chest safety committee has to worry about the specimens you're bringing and the materials, whether or not they're hazardous or non-hazardous materials. And so that's a big arrow. They really focused on that. The peer reviewers, they're worried about this too. They think about the availability, and the beeline scientists think about it as well. And then this is also, the outside reviewers are judging whether or not you need chest and whether or not you have a good plan. In this case, the proposers decided to write just 2 sentences. They're going to do something with superalloy. You can see I redacted some of it, so none of us steal their proposal. But they also you can provide a linked document. So you can save yourself a lot of typing time or copy-paste by just providing a document, which this group is then going to refer to later on and show you. So they did a pretty efficient job of entering only the minimum amount of material, but having an outside document. So let me zoom in on the specimens and materials. Now this is a different proposal. It's not one studying metals. This is pretty clearly, just give a look at that. That's a chemistry proposal, okay? But look what they did that was really helpful for safety committee. 5 ml of 10 millimolar? Yeah, okay, I'm a physicist, by the way, okay. So, and look at that name, it's great. I was like, supercalifragilistic. It means something to some people. But what's important is, they're trying to figure, I hope the safety committee is looking at this and deciding this stuff, when it comes in the lab, won't kill Ernie or anyone else, right? So this is the information safety committee needs. This is really excellent. It shows quantities, names, pH, state, maybe even safety data sheets and other. Super important for safety committee, and also impresses the reviewers that you have thought very carefully about yourself. You know what you're going to do. Another example of let me jump to scientific justification. So this is now a different section, and this really is, it tells the reviewers what you're going to do and why it's worth doing. So this is a really good one. I like this example because they write very clearly. The aim of this work is twofold. One, to develop a fundamental understanding. Two, to perform a proof of concept. Very clear. And then they go on. We're going to do low cycle fatigue tests. Number two, we're going to do high cycle fatigue tests. And this conclusion is just awesome. Okay? Both parts are one step of a unique opportunity to couple high energy diffraction with tri-beam blah, blah, blah. But what's so cool is that it tells the reviewers, it tells the people that are reading this proposal, we are trying to do something brand new. This is a risk. We're taking a risk. We're doing research. We're seeking new information. No one has done this. You don't see it, but I've redacted it. And so this is really a strong statement that you want to put on the work you're doing. If you can make a strong statement, make a strong statement. If you can't, you're going to fake it. But I didn't say that. Did I? No, I didn't say that. But make as strong a statement as you can about how hard your work is or how much you're going to learn. This is the place to do it. Don't be shy. Here's a different scientific justification. Now, this is back to I think this was a chemistry. Yeah, look at all the chemistry. So this is a chemistry proposal. I don't know if it was the same one. This is a fantastic science justification also. But look how many words, right? You're all looking at this going, yo, Ernie, you're not going to read this to us, are you? No way. Right, but I read it, right? And I read it and I took a look at it, and what each paragraph is doing is something really valuable. They're identifying a system of interest. They're talking about questions, the exact arrangement, blah, 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 is still unknown. They're talking about questions they want to study. They're talking about challenges that have to be overcome, challenge due to the small energy difference. And then at the bottom, they're identifying critical questions, and the critical questions will be answered. That's fantastic. My only beef with this, and in a few slides I'm going to show you, is that it took me reading the entire paragraph to get to critical questions. I really would have liked to see the first two words be critical questions. Then I would have said, oh, this paragraph sounds great, I want to read this. So I'm more of bring it front in case people don't read the whole thing. Sorry, I'm critiquing some people you know, but okay. But the external reviewers, they also may not want to read all these words. And so sometimes it's good to summarize it a little bit. I'll show you in a few slides. Part of the proposal is publications. This is used by the outside reviewers to determine the expertise of the group. If you have a lot of background in the work you're doing, it'll show up in publications. It's even okay to list work, like it says, it asks for publications from work done at CHESS, because we want to know what you've done at CHESS. But it's okay also to mention work that's been done elsewhere. We're not that crazy about it. You can tell work, because it tells us that you've done work elsewhere, that's fine. And this is really important to peer review and to the beamline scientists. They know that you've done some work. They can look at the data you've taken before and then predict whether you'll take good data in the future. It's very important to the outside reviewers. Here's another, so there's another section, I'm working my way down. Experimental plan. This is a proposal that I really like because they start with a summary. They want to do 4 days. I mean, this is an experienced group. They know how many days they're going to need. You may not at the start, if you haven't visited CHESS before, but over time, you might know you want to try 4 days of cyclic testing and 1 day of extension testing. And then they go on to explain part 1, part 2. Very well organized, simple. They've got fantastic, so this must be a group that's used this before. They know exactly, So they're predicting how many samples and how many hours. They're down to the hour. That's pretty specific. So it's very nice to read that. But again, talk to the beamline scientists. They can help you estimate how much time you will need. This is the experimental plan I wanted to come back to because I just like the way it's written. Again, it's a lot of words, but look, each paragraph says, this is the experimental plan. These are the expected results. This is the experience of the team. Really easy to just say, I want to read that. Okay, I'm not even going to read that. I don't care about that. But I can jump in this paragraph. Oh, I want to read that because that's the expected results. Well, that's the team experience. So it's nicely organized, really simple way to organize it, and it makes it easy to read for the scientists, peer reviewers. It really tells the outside people that you need CHESS and that you have a really good plan. It's also possible to, on the website, gives us lots of space where we can, it asks you for additional needs, if the special equipment you need. Is your hand up?
My hand is up, Ernie.
Yeah, go ahead.
Can I a special input as I'm gonna put my safety committee hat on?
Safety committee hat. Okay.
Talk to your beamline scientist before adding to those additional needs.
Okay.
You might actually flag yourself for a safety committee hazard.
Oh, okay. Okay.
Yeah.
Yeah.
Oh, yeah.
I almost understand that. But what I was gonna say.
Talk to your beamline
So to the
scientist.
scientists, yes, because they may have, right, so if you use the Cameroon field hood, you may already have the safety committee have to oversee your work.
Yeah.
I understand what you're saying. But if you need to use the minus 80K freezer, or you need special bench space, there's quite a list there. I'm sure it's not complete either, but there's a list of special equipment you might want to have, or space you want to have available when you come visit. So that's part of the proposal as well. You are done, believe it or not. That was it. That was the 10 items. I know it seemed like forever, but that was the 10 items. You've gotten to the end. You have two choices. One of them is you can actually read down. It's scrolled up at the bottom of the page, of course. You can read down, and if your proposal complete, or if you want to change something, you go back. Look at this in red. You know, once you submit it, you're not able to edit it, and you can't delete it. It's there forever, right? The IRS. Okay. So once you're all done, once you think it's all ready, then you submit it. And then what happens? Then you wait a little while, not too long. The user office, Caitlin Towner and others, will turn your proposal into a project. That's just a different name for it once it's in the system. And it'll have basically all the information that was on your proposal, except for one thing. Every time you submit a proposal, automatically is created this thing called a beam time request. So BTR, everyone at CHEST says that all the time. That is the request to actually make a visit to the lab. So every time you visit, you might have a different BTR, which picks a certain date, hazards review, it might be scheduled or not scheduled. So given one proposal that's in the system, you may come several times. How many years? 2 years, Chris tells me, good. 2 years it stays active, and it can be renewed, I think, also. Okay, I'm not, don't yeah, okay. Ernie's not saying all this. Ernie may not know what he's talking about. Okay. But you'll have beam time requests, and these are one-time visit forms, and get specific about what equipment you actually need to be on the beam line, and what dates you're going to cover. Let me end with when. When do you do all this stuff? So there is a plan. Caitlin and others in the user office keep very up to date. So under the users tab, under X-ray run schedule, there's a page that opens up that has two types of information that might be useful to you. One of them is we have these very cryptic calendars that actually show you when, in dark blue, it shows you when there is days when the machine is being run for X-ray users. So that's called an X-ray operations calendar, and there you can click on these PDFs and it opens it up. And good luck figuring out how to read that. Okay, it's really crazy. But your beam time scientist can help you read that. What I'm going to talk about is proposal deadlines. This is quite important, right? So when you submit a proposal, when will you expect to hear from us? So if you click on that link, you'll come to a page like this, which shows you, so every year, CHEST has 3 running periods. I'm looking to see if you correct things. 3 run periods, and so this is for the fall of 23. And there'll be some dates here that come along. There's a call for proposals and beam time, May 1st, that passed. There's a deadline for submitting the proposals, which is August 8th this year for this cycle. There's a beam time request deadline. There's a request for something that relates to Gen environment, rapid access. I think that's for Flex and for biostats. That's a special type of proposal. And then the run cycle begins, that dark blue period, October 18th to December 20th. That's when the users, you, would come and schedule time to come visit the lab and do your research. So just to know, there's schedules out there. I'm going to conclude with just saying that I was showing you that this menu shows up on all of the website pages. Once you get through writing that proposal, then you might start thinking about, you know, when am I scheduled? When am I going to come? Have I satisfied safety? Are there technical resources I need? And then you're traveling, and then you're sending your samples. So there's a whole menu of things that will help you. It's not useful for me to just run through those now. When you need it, the information's there. And so I'm going to end with Caitlin Towner. You'll meet her tomorrow. Mike tells me you're going to overlap her a lot tomorrow. And she helped me.
Today, actually. Okay.
Today, actually. Oh, there you go. I didn't get a picture on it, I'm sorry, but she sent me this email. She said, convey this. I asked her, what are the takeaway messages? She says, really important to remember that not all information is immediately available. So I'm talking as if you have to know it. But it's not always available. It's okay to say, I don't know. I couldn't fill it in. I don't know yet what the answer is to that. We'll work with you with that. She says here, communication is key to successful collaboration. So we feel that the Light Source is collaborating with our users. You're encouraged to reach out to the user office and any of the Beamline scientists with any questions or concerns. And there's a generic email address for the user office that a number of people monitor and answer questions. We try to answer those 24/7, I think, right, Mike? 24/7?
347?
24/7?
24/7, absolutely.
Yeah. We try to keep up with it.
365.
365. You can call Mike any day of the year. Right, Mike? Oh, shut up.
You can call.
You can call, absolutely. We're gonna stop there. This was supposed to be a discussion. Any questions? Or anything to add?
No, thank you.
Okay. No one wants to submit a proposal.
But what are, often, what is there a common reason why some proposals have been rejected? Like what do you think?
Rejected? Oh, that's a great question, and I can probably almost answer it. I think that if information is missing, I don't think things, rejected is not a word we use. It's more like, oh, we had to call you up. We saw you were going to bring hydrofluoric acid, 55-gallon drum. We think you're wrong. We think you probably meant 55 milliliters. So nothing is rejected, but it's definitely checked up on and made more complete or it might be, if anything is rejected, it's more like, oh, we can't do that. You need to go to another light. We actually cannot, you want to go 20 to 70 degrees, we can only do 20 to 40, and so you'd be better off going maybe to another light source that can do 20 to 70. So there might be technical reasons why a proposal might be not ever get any time, which would be like being rejected. When you submit something and you never get any time, that would be the equivalent of being rejected. But it's mostly because it wasn't appropriate. We couldn't serve you. We couldn't give you the information you needed.
What?
That answer that. I'm sorry.
Oh, yeah.
Yeah. But I'll take your name, and if you submit one, we'll reject it. Just so we know what your experience is. And then fill out this feedback form, please.
Whether a user is an undergrad or grad student or postdoc or the PI, who should be submitting?
Oh, that's a super question. Usually a faculty member or someone who's been a PI on a funded award will be the principal investigator. But in fact, usually it's the grad student who wants to do the work who becomes the most active and useful person on the proposal. I don't know, that's generalizing. Chris, what have you found?
We get proposals from PIs, grad students, postdocs, everything in between.
Yeah.
Okay.
So it doesn't really impact anything who it comes from.
Okay.
Yeah.
What about undergraduate specifically?
Undergraduate specific.
The knowledge, academics, and context work.
We have undergraduates come do research in the lab, but pretty much, I don't know that we've ever seen one submit a proposal and walk in the lab and do research. There's too high a barrier to get started. But undergraduates can collaborate with Beamline scientists. That's a really good way to get in to do some science. Chris, anything better? Jenny, anything better for undergrads? There are a lot of undergrads in the lab doing work. I just don't know that they submit proposals and get them through the system.
We actually do have a couple of undergrads that submit
There you go.
proposals, but they usually do it with their PI as the main investigator, but oftentimes if it's, they'll guide them through the process, but we do have undergrads that submit,
Yeah, there you go.
at least at Sector 7.
You mentioned
Shout it out, come on.
You mentioned previous work experience with chess, for example. So if, let's say, our lab group does not do that type of work, and then maybe we're trying to get into it, what kind of advice would you have for that first time? Because you mentioned like that if you've done stuff in the past, you're going to get good data, reliable data that you trust. So what kind of advice would you have?
Well, the advice, we do have lots of groups that are first time, right, Chris? Lots of groups, and so they are working with a beamline scientist is super valuable for you, because, then it's someone who knows the equipment, who can maybe work with you to guess how much sample you need to bring, things like tangibles. I sort of lost it. If you've done any lab work, if you've done any other background work, or if you've read papers like that are the type of work you want to emulate, that's helpful. Nothing beats hands-on experience. I'll tell you that, right? So there's no, use Chris's beamline for dummies right up. It won't get you anywhere because you still have to come in and do it the first time. And so, Chris, advice for first time.
Yeah, I mean, something I have had some new user groups do that I've worked very closely with is in that section. They won't have any papers, but they will be able to say, worked closely with beamline scientists to discuss the project. So that way it communicates to the reviewers that the group might be new, but they're leaning on the experience of chess staff. And that's really, I think, what they're looking for. Thank you.
So, if you were have a little bit more experience with it, can you still request help from the beamline staff?
Oh yeah. Yeah, I think if I'm going to generalize, but I know from my experience, I was a beamline scientist for many years before getting into this silly management. But anyway, the more experienced users actually leaned really heavily on the scientists because they wanted, I remember, many groups, they're like, Ernie, remember I had a 1 millimeter square beam with a certain intensity profile? I need that again. So they really lean because they want the conditions to be the same or better. Like they may call up and say, Ernie, I want more intensity than I had last time, or I want a filter that you didn't have that I really need this time. So the more experienced users actually lean on this beamline scientist. It's hard. You can tell how many times I've said it. It's hard. It's hard for people who haven't been in the lab before to feel that they're imposing. They're not imposing. It's really good to get in contact with beamline scientists.
We would much rather answer questions and be helpful up front than have you come and have your experiment not work.
Oh yeah.
We would much we like helping you. It's why we're in this job.
So as the expertise, increases, the questions get more specific. The parameters.
Oh yeah, correct. You'll get more specific. You'll get really fussy. Like after you bought your 10th portion, right? Your 11 is going to have exactly the color leather you want. I'm saying, yeah, that's the way users have been with me. The more they come, the more they're like really fussy. Like, oh, Ernie, you changed something. I had to change something. Oh no, you can't change it. Yeah. But yeah, for beginners, you really should talk to someone. Get your hands on the hardware. That's really where you're going to learn how to do things.
Question. So in terms of funding, are the users funded by their university funding, or is CHESS providing funding for travel and lodging, etc.?
That's a great question. So I'm not part of the CHESS management anymore, actually. I can tell you that. But, so I don't know if they have funding for users to come travel to CHESS. I don't know that anymore. I'm looking at Chris because I'm leaning on him a lot. But no, getting some. So I don't think you're going to get funding from CHESS.
Okay.
But certainly people have funding from many different universities and funding agencies. Jenny's going to say something.
I was just going to say that if by funding you mean getting to CHESS and having a place to stay and whatnot, then no, unfortunately, we don't usually provide that kind of funding.
Okay.
By usually, I mean occasionally we'll host workshops where you can kind of interweave that kind of thing in like data collection into it.
Okay.
But to let you know, Beam Time is absolutely funded by most of the partners, depending on what project you're working on. So my Sector 7 is funded by the NSF and the NIH. That means that anytime you bring your experiment there, that Beam Time, which costs upwards of about Can I say, Ernie, is that all right if I give a number?
Yeah, sure.
Crazy. That's about $1,600 an hour.
That's a
tough.
discounted rate.
But that is actually paid for. But yeah, if you're curious about funding, I would say reach out, and there's the worst thing we can say is no. But we can point you in the right direction.
The other.
Sorry, Chris. Let me come back to the man here that said he had no experience. After tomorrow, you have experience. You're going to have work down on the floor on the beam lines. So you write down, hey, we know how to do something. We came here and did something. Chris, go.
And just to build on that too is, since COVID, all of our beamlines can be uploaded remotely too.
Yes.
So if you have a group of people and only have funding for 1 or 2, that's perfectly fine. The others can stay at home and still do the experiment remotely. Or if no one can travel, you can mail your samples and we can do all the mounting for you, and you can still collect and participate remotely. So the barrier to participation is fairly low for a lot of experiments.
Yeah, thanks for adding that, Chris. I forgot to mention.
Thank you.
Excellent questions.
I have another one, but it's less related to this. I wasn't going to ask, but it has to do with, let's say we have data, you have a bunch of data. As far as analyzing data, usually I'm so used to analyzing my own data, but some of this stuff, especially we were talking about 3D images and stuff like that, I feel like, I don't know, I was wondering if there is software that's specific for the things. To where
I put him in the audience. That's an excellent question. But that's part of a facility. Yeah. Is there software you can beg, borrow, steal?
Mm-hmm.
Yes.
Yes.
Absolutely. First of all, as you were asking the question, I leaned over to Mike. I was like, Mike, this is what I like to do. Data analysis, yes. So for all of the beamlines, we are continuously trying to automate data processing and to try to create pipelines and workflows and whatnot. For Sector 7, which is the biological squishy stuff, we have already set up automated processing, which basically spits out what you need to know at the end, and you can take it and go on your merry way. But every beamline, the scientists want you to have the best data possible. And if that means also helping out with data processing and being able to reduce your data or to work with you to actually get figures and whatnot, every beamline scientist wants you to have what you need in the very end. And so we'll guide, we'll teach, very happily so.
Yeah.
And constantly upgrading to make sure that, especially as new techniques come on, people bring crazy experiments. We're like, I don't know how we're going to be able to process this. We'll build a pipeline.
Yeah, pipeline is just taking a piece of software that exists and putting it together and letting your data flow through it.
Yep.
When the dinosaurs roaming the earth and I was a PhD student, I had to write all my own analysis code. That was a waste of 3 years of my life, probably. But now there's so many excellent packages, right, Chris? You can speak to software. Do your users take software home or use online?
Yeah, so pretty much all the tools for spectroscopy are just freely available online. And so it's the same stuff we use at the beamline. And so we'll teach you some of that when you come at the beamline, and then probably after supporting users at the beamline, the next thing I spend most of my time doing is helping with data analysis. So it's something that we absolutely do all the time.
And it helps having a conversation, right? And the beamline scientists will oftentimes help you collect data, but they don't know your system as intimately as you do. So that'll be a conversation going back and forth.
Excellent question.
Great. Oh, I got excited.
Yeah.
Oh, damn.
You got it in. Oh, Mike's giving me the tea for time. Thanks for the great questions. That really made it worthwhile.
Thank you.